live on YouTube.
Okay.
So my screen is visible now.
Yes, sure.
There's something on chat.
On chat, that was the question about YouTube. Okay, we wait a couple more minutes.
Dima, I see that you're talking, but I don't hear anything.
Okay, so I'll repeat. Hello, everyone. Thank you for staying with us till the last day. I'm glad to present our first speaker for today, Avraham Aizenbud from the Weizmann Institute. And he will tell us on point-wise surjective presentations of stacks, or why he is not afraid of infinity stacks anymore. Please.
Okay, so hello everyone. Yeah, so thank you very much for giving me the opportunity to talk here and for the conference in general. So the Zoom format is working surprisingly well. So I did actually hear many lectures and had fun. Yes, so Joseph, I also want to thank you. You all probably heard me saying it several times, so I will try to be short. So just want to thank you for the wonderful experience of studying math from you for the last 20 years and still counting, more than 20 years and still counting. And it is really wonderful, and thank you very much. Some comments about the talk. So if some of you heard the talk with the same title some time ago by me, so it's just the same talk, almost no difference. Some technicalities are more finalized now, so you don't have to waste your time again. Also, the talk will be rather elementary, I think much more elementary than most of the talks that I heard in this conference. So I will spend some time explaining what are stacks and like some background on them. So yeah, maybe for some of you it will be better just to watch the recording in double speed or something like this, because there will be some introductory things. Yeah, so the talk will be about mathematical results, so about the first part of the title, but also I somehow working on these results and the results itself change my view on the topic, and I will try to convey this too. And there will be nothing infinity involved in the talks, no infinity stacks, no infinity groupoids, but still somehow some of the basic ideas of this higher category or higher mass, like the ideas somehow went inside some of the ideas of the proof, and I will try to say something about it. So maybe in short, there is this joke about the way to think about 7-dimensional space is to think about n-dimensional space and plug in n equal to 7. So in this category theory, somehow it makes sense way before 7. So maybe 1 or 2 sometimes is more convenient to think for general n and plug in those small numbers, because those small numbers 1 and 2 sometimes already are big enough for things to become complicated without a system. Okay. So let me start with some short motivation. In representation theory, we often have a situation of a group G acting on a space X. For this moment, X can be just think of a set, but some geometry will be involved soon. So G acts on X, and we want to consider some objects on X which are G invariant. So maybe the simplest examples are invariant functions, but then you can go to invariant distributions, invariant sheaves, or equivariant sheaves, equivariant vector bundles, D modules, or whatever, many options. And so let's, with this obvious example of functions, so invariant functions are just functions on the orbits. So we don't really care about X, you just care about the set of orbits. So in general, you can say that you don't really care about X and about G separately, but you care about the quotient, X modulo G. So if you just think about functions, and you just care about the quotient of the set. But of course, if you want to do some more complicated geometry, so bundles or even distributions sometimes, or even functions, but not invariant, but equivariant, then you also want to remember more of the structure of G on X. Not all of its structure, but some of it. And here where the notion of groupoid become very useful. So you want to consider the quotient groupoid. I will remind what it is in a few moments. And your space of invariant or invariant whatever depends only on this groupoid. And of course, if you have some geometry involved, so this is some kind of geometric object, which are often called geometric stack or algebraic stack if it's algebraic geometry which is involved. Okay, so now let me give a short reminder on groupoid. So groupoid is a small category whose all morphisms are isomorphisms. And maybe the most basic example of groupoid is BG. This is what give it a name. So it's you can think of groupoid as generalization of group. So if you have one object and some group of automorphism G, then this groupoid is called BG. And to study such groupoid, it's more or less the same as to study groups. And slightly more general examples, the ones that I think we're most interested in, is you have a group G acting on space X, and then you can define the quotient groupoid. So objects are points in G, and for any two objects, maps are elements in G that lead one to another. So the isomorphism classes in this quotient groupoid will be just G orbits, but we do remember a little bit more information. And practically, I more or less will be interested only in such groupoid, but it will look weird but I don't want just to think about the pair G of G and X, because it's too much information. So sometimes the same groupoid have different realization, and some of them are even not like this, and they're more convenient. So this is the reason, at least for me, that's why we really want to talk about groupoids and not just group acting on a space. Okay, so now let's try to do some geometry. So we basically want to repeat the same things, But now instead of sets, we want to have some geometric objects, and in this lecture it will be schemes. So we have a notion of groupoid object in the category of schemes. So we just repeat the definition of category, but everything is now scheme. So the collection of object is a scheme, and the collection of morphism is a scheme. And this is convenient to do when we do all morphisms, not morphisms only with fixed beginning and fixed end, but all morphisms together. And then we need to have two maps, the source and the target map from morphism that's saying from where it goes and to where it goes. And we want those maps to be smooth, so it makes sense to require it. For example, it's what happens in quotient groupoid. So this is what you usually want. Like groups, you want them in algebraic geometry. Group scheme, you want it to be smooth usually. So this is also, you want the source and the target map will be smooth. And now you want additional data. You want the identity map for any object you have identity over this object, so it's pointing more over this object. For any morphism, you have the inverse morphism. And the most interesting thing is, of course, the compositions. For any two composable morphism, you have the composition, and this is a way that you can write it, that you have a map from the fiber product to more. Of course, now one have to write some axioms. And of course, we can just read the definition of category, and each of the axioms we write in this language of some commutative diagrams of morphism. But we also can cheat. How do we cheat? We just pick up any scheme and consider S points, or S points of a scheme is just map from S to the scheme. And then we get sets. So ob of S is set, everything is sets. And those maps that we had before are just maps of sets. And now we want to ask that all this data will give a groupoid. So this cheating is, at this point, is just convenient trick. You don't really need it, but it's also important because this is part of this idea that often it's very convenient to replace object by the functor that this object represents, and or many formulations become much simpler. Okay, so now the collection of all groupoids is not just a category. So of course we can think of it as a category, but it's not a good idea because functors between two groupoids also form a category. So the collection of all groupoids is two category, and we can carry this out, at least naively we can carry this out to the geometric setting, and we can talk about the two category of groupoid objects. And okay, so morphism is just functor is just algebraic morphism from ob to ob prime, and from more to more prime that satisfies something. And again, there is a hard way to say this something, and there is a lazy way to say what is this something. Anyhow, it works. So we get some two category, maybe not very nice one, but a two category. Now another way to think about the same two category, as we said before, it's nice we can replace object by the functors that they represent. So we can also replace groupoid objects by the functors that they represent. So we take, if we have some calligraphic X, so we can which is groupoid object, we can take chi of S. This will be functors from S to X, sorry, and functors from S to X form a groupoid. So we get so overall we associate to any groupoid calligraphic X a functor from schemes to groupoids. So, and we can identify calligraphic X with this functor, and we can define a groupoid object by a functor that can be or two functor to be more honest, that can be obtained this way. So alternative approach to the same thing.
Rami, in the right-hand side, do you mean by S the category of schemes over S?
No. By S, I mean a specific scheme, and I define the notion of functor between two groupoid objects. So also I have the notion of functor between scheme and groupoid object. So this right-hand side is a rather small groupoid.
What is functors from scheme to groupoid object?
It just maps from ob to ob prime, or to from S to ob. Just read this definition, but you don't have more. So, more is trivial. More is equal to ob.
More is trivial. So scheme is a trivial groupoid, as a groupoid with trivial morphisms.
Yes. So more equal to ob, and source and target are both identity, and composition is identity. So yes, and as a set is just a maps from ob to from S to ob, and as a groupoid, you also need to define what are morphisms, and this is mapped from S to more such that something happens. Okay, Dima, do you approve? Okay. So we have this functor, so we can think about groupoid objects like inside functors. Okay, but all this approach have a big problem. Is that the notion of functors between two groupoids, and even the case between scheme and groupoid, which we see here kind of the most important one, is not local. It's not local on S. So if we have the groupoid object X, and we can write it as a union of two open sets, even the Zariski open sets are already the problem, so two Zariski open sets. We later want a tal, but not Zariski. And when I say open sets, I mean I just take open set in ob and the corresponding full subcategory. So all the morphisms that over this open set. And now I have two functors. I want to construct group functor from X to Y. So I have two functors from U1 to Y and for U2 to Y. And I want those two functors, of course, agree on the intersection. Otherwise, I cannot expect anything to work. But they often. But what does it mean for two functors agree on the intersection? So we can restrict them to the intersection. So we get two different functors. We can ask them to be equal, but this will not be fair thing to ask because they are the two objects in a category. So we want to ask them to be isomorphic. And usually you probably know that you have to ask some higher coherence relations, but in this case, I'm just talking about two open sets, so no higher coherence relations. And still, I want to be able to glue those two morphisms, and I can't. So it's very easy to find an example. Maybe I should have write it here. So for example, you have the trivial groupoid C star, and you have another basically realization of the same groupoid where we expect it to be equivalent. Of course, it's not formally, it's not, or by this definition, it's not. Of takes the objects are C star and the morphisms are also C star, but the source and the target maps are basically given by Z square. Now I need to. So the idea is that okay, it's a quotient groupoid. You have C star acting on itself or GM acting on itself by multiplication. No, sorry. You have just you identify any element with its negative. So with Z with negative Z. So you have for any element, from each element you have two morphism, identity and some isomorphism to its negative. And this groupoid, you have a functor from this groupoid to C star by squaring, but you don't have an inverse functor. You don't have a square root. I know it was a bad example for this. So yeah. Okay, it's also an example, but not in the Zariski topology. Here you have to talk in a tal topology, or if you work over analytic manifolds, you can just cover it by two open sets where you do have square root, and the square roots maybe does not agree, but they agree up to a sign. So in the two functors should be isomorphic, and in this example they are not. Yeah, of course, there are also counterexamples in the Zariski topology. I'm sorry. So we have this problem, and now we want to solve it. So we want to change the definition of a groupoid, object, or replace the notion of groupoid object by another notion, which will not have this problem, which will behave locally. Yes?
Covered by subgroupoids? Or just some cover?
Here before, covered by subgroupoids, and they even want like full subgroupoids. So U1 and U2 are, say, open sets in ob, and this and the corresponding morphisms will be just like the pre-images, all the morphisms that both source and targets are inside U1, and so like full subcategory.
Okay. Yeah, just wondering, like,
Hmm?
if you have counterexamples. I was just wondering if you have a counterexample.
Okay. So whenever we have something which is not local, we can make it local, and this is called stratification. And I think in this context of like groupoids, which is like the higher level, is sometimes called stackification. Though I think maybe now people start to call it again stratification because yeah, after you go to many levels, so you don't really care about it anymore. So given a groupoid X calligraphic, we can stackify it and make out of this a new functor, a better functor. So in this definition, we think about X calligraphic as a functor from schemes to groupoids. And now we can make out of it a better functor, which we'll call X Gothic, which will be a stack, which will be the stackification of X. And how we define it? So the idea is like this: we want to define these objects of like the groupoid X of S. So we want to define what are all the objects. Yeah, I don't give here a complete definition. I just give the main idea. So we can start with naive guess as calligraphic of S, X calligraphic of S. But this will give us not enough objects because there are some things that locally can look like objects here, but they are not here. So what does it mean locally? We have some cover of S. So before we had the Zariski cover, but we want to be more general, so we take a tal cover of S. And then we want to consider object in S prime, in X calligraphic of S prime, together with some additional data. So what data? So what data we need to give on an object on S prime, or sorry, on a morphism from S to our stack, or to from S prime to our stack X calligraphic or our groupoid X calligraphic, what data we should give on it, such that we would expect it to go down to something that lives on S. So this is called descent data, and you probably all know or at least saw it in many cases. So if it was a Zariski cover, so for each intersection you want to give isomorphism, and for each triple intersection you want to require some coherence relation. And since it's not a Zariski cover, but a tal cover, so instead of intersections you do fiber product. So I will not write explicitly what it means, but say it's something of that nature. And now we can say that, and okay, I only say what are the objects, but similarly you can define what are the isomorphism. It's a little bit more complicated, but similar. Now I can obtain such functors. So for any groupoid object, I can obtain another functor, X Gothic, and I can just declare that functors that are obtained in this way are called algebraic stacks. So this will be the definition. Okay, I can try to say it, but this is not correct definition. But it is correct that any functor that are obtained in this way is an algebraic stack. What is not correct that not all algebraic stacks can be obtained in this way. So at least at the first level, we're only interested in such stacks that can be obtained in this way. But if you want to know the tools, so in this language, you can still say what is a tools. So basically, you repeat all this procedure, but you allow your schemes, you consider a groupoid object, but not in schemes, but in a more general thing that's called algebraic spaces. So you allow the schemes to be orb and more to be algebraic spaces. Specifically, you can assume that orb is a scheme, but it's important to allow more to be algebraic space. So of course, you can ask me what are algebraic spaces, and I can give a circular definition. Algebraic space is an algebraic stack whose automorphisms are trivial. But this looks like a circular definition, but in fact it's not, because we can just do it for stacks obtained as above, as in these definitions, from actual groupoids in schemes when both orb and more are schemes, and it turns out to be enough. So you have to do this procedure twice, but not more than twice. So you use this definition in order to define like some class of stack. In this class, you identify algebraic spaces, and then you do this procedure again. And this is it. You don't get new algebraic spaces. So it's a bit annoying, so you can ignore it or you can remember it. Depends on what do you want. Okay, but we still have a problem. So okay, we did this procedure, but we don't know what it gives to us. We start with a groupoid object x, and we know what is x of s, but we don't know what is x Gothic of s. We of course have a functor, and this functor is fully faithful. It's easy to check, but it's not essentially surjective. So the right-hand side is larger than the left-hand side, and this kind of makes stacks harder to approach. And for me, this point was kind of hard point. I understood very well what are groupoid and groupoid objects, and I feel very comfortable with them. But how to work with stacks and how do I know whether I get all the points? I didn't know. And so what Joseph did, he made me much more happy by explaining one nice trick, that if the stack is a quotient stack, what we are usually interested in, and usually we're interested in linear groups. So it's a quotient stack by action of a linear group. There is a trick that we can replace this linear group by GLN. So because any linear group is subgroup of GLN, and then there is a trick that you can extend the subgroup, change the space, and don't change the quotient. And GLN have no higher Galois cohomology. No first Galois cohomology. And this magic happens, and it means that this map is wants to be onto. What do I mean? So it's not reasonable to expect this map to be onto when S is not a field. So this map is always onto when S is algebraically closed field, but S is something geometric, so it's okay. Yeah, map from S to groupoid. It's something it doesn't have to be given globally from map to S to object. I can live with it. But when it's one point, of course I know that one point is still not a point. It has some metal covers, but it's hard for me to understand. So if S is a field, I prefer to have a presentation of the stack where I will see all the points naively. And indeed, if it's quotient groupoid, it happens. And this is very satisfactory on level of applications because these are the applications that we care about, but it's not very elegant. So we want it for more stacks. So here is the good news. If we have any algebraic stack, then we can represent it by a groupoid object, opsic more, comma more. And here, to be general, more have to be algebraic space, but we don't care at this point. So maybe this algebraic stack, so by the approach that I just told you for algebraic space, it's of course not the standard approach, but I think it's good for this talk. So algebraic stack, by definition, it came from some groupoid, by this definition. So maybe this groupoid does not represent it well, but we can choose a different groupoid that will represent the same stack, same meaning equivalent, yes. Such that this functor will be an equivalence of categories. In what generality? Here we have to be careful. So if we don't put any assumption on the stack, or I forgot to say, so I say we don't put any assumptions, except of some assumptions are always there. So everything is a finite type over some Noetherian scheme Z, S. So you can assume S is just spec Z. So, and everything is finite type over Z. Or S can be other Noetherian scheme, but fixed base, and everything is finite type. Somebody want to ask a question?
Yes, Rami. So here, calligraphic, Gothic X comes from some calligraphic X, and you replace calligraphic X by another so that you get this equivalence?
Yes, so Gothic X, only what I know about it, that there exists some calligraphic X that do the work, and by definition, or by the definition that I gave for scale stack, it's not the standard, but it's of course equivalent. And I want to choose another calligraphic X, yes. So I don't claim that any presentation is good, but I claim that there exists a good presentation. And here one has to be a bit careful, so it's not true in general. It's actually not true in general. You can find very easily. So if you take BG when G is an elliptic curve, this stack will have no good presentation that will work for, say, QP. But you do have a presentation which will work for all, say, finite field, real closed field, which I'm interested in R specifically, of course. And also here we didn't check it completely. Yes, it's some comments that we got, but it's true. Yeah, so pseudo algebraically closed field is also good, and probably many other fields are also good, but not any field. So general local fields are not good. Now, if you want any field, what?
I have another question. Maybe I'm off, but I get the feeling that this process of taking a calligraphic X and getting a Gothic X is something. It's like taking a group and getting out of it its commensurability group. Is this a good analogy? Yeah.
I'm not sure.
That's okay.
I will need more, more input for that, so maybe after the talk. Okay, so if you want almost no limitation on the field F, so I think in practice you can do it without any limitation of the field F, but for now F should be perfect. And then you need some assumption on X, and the assumption that we need is that it's automorphism group. So for each object, say in the stack, we have automorphism group, which is algebraic group. So we want this group or algebraic group scheme, and depends on what kind of object. So we want these automorphism groups to be linear groups, linear algebraic groups. And this is called QCA stacks. I saw it in a paper. I forgot also what was so. Okay, so this is called QCA stack. But I think all the authors of that papers are here. So I'm just not sure that I remember what is the correct set of authors. Okay. So we either need to put some condition on the stack or some condition on the field, but then it is true that we have a very nice presentation. Okay, so this is the way I like to think about this result. It's not the way you standardly formulate it. Okay, so one comment here, but you don't see it, yes, sorry. Oh, now you see it. Now you see the comment?
Yes, we do.
Yes. So once you know everything for a field F, for some field F, once you know that such map is onto, then instead of F, you can consider any Henzelian ring with F residue as a residue field. So for example, if you know something for finite rings, then you automatically know it for finite fields, then you automatically know it for all finite rings, and even for, say, ZP. So we specifically, like originally was interested in this question for ZP. We wanted to be able to count ZP points on a groupoid, on a stack, and we understood how to do it for groupoid, but then we say, okay, we don't know the other pieces and we don't know what are them. So you can find a presentation of any stack, for me, everything is finite type, that will be good over, will be like pointwise onto over all ZPs, and then you can get nice counting results. So this was our first application that we had in mind, and then there is another application for R, but anyhow, I do expect it to give some applications because, okay, of course, in the process of proving this theorem, we understood that, okay, it's not that bad that stacks does not have, sometimes, or some presentations are not onto, because we understood how to work with stack even if the presentation is not onto, but it's still easier sometimes to work with onto presentations because it's easier to prove theorems. Yeah, so before, for me, it was a psychological importance of this theorem that now I better understand what it is about. Maybe now the psychological importance is become less because after proving this theorem, I understood better what are stack, but it's still practically important. I think this theorem, we have some applications. Okay, so now how to reformulate this theorem. So usually we don't present stacks by groupoids, but just present stacks by schemes. So I just want to remind what does it mean. Yeah, so usually people define stacks a little bit different. Of course, equivalent, that it's some functor from schemes to groupoids that satisfy some conditions. And one of the conditions, or maybe the main condition, is that it can be represented by a scheme. Oh, not the main, but an important condition that it can be represented by a scheme. And what does it mean? That we have a map from what is the representation of a stack by a scheme. It's a map from a scheme to X, which is surjective and smooth. So what does it mean? It means that when we do a base change for any scheme S, we consider this map should be surjective and smooth. So here again, there is small asterisks. This base change, if S is a scheme, we do this base change. We don't get stacks, but we can get algebraic spaces. So this Fourier product is not necessarily a scheme. And so one have to define what is a smooth and surjective map of algebraic spaces, which is not that fun, but not that bad. Anyhow, we will ignore it for the moment. And so we understand what is a presentation by a scheme and how it's related to presentation by groupoid. So once we have this map from X0 to X Gothic, we can take the Fourier product and call it X1. And we have two maps between X1 and X0, projection to the first coordinate and the second coordinate. And then we see that what happens actually that we got a groupoid. So X0 plays a role of orb and X1 plays a role of more, and source and the targets are the two projections. And okay, now one have to explain how to do composition, but it's very easy using this definition. And then we get a groupoid that represent our stack. So this way the two approaches equivalent. You can represent stacks by schemes or by groupoids, and it gives you the same information. But okay, intuitively for me it was easier to work with the notion of representation by groupoid because then I actually see the stack as a groupoid. But practically it's much easier to work with the notion of representation by a scheme because there are less things to take care of. Yes, you don't need to remember all this data of more and source and target and composition because they're all encoded in fact in this map from X0 or from orb to X Gothic. Now, if you want, you can go to the other extreme and get much more data, which is of course not needed because it's all encoded in the original data, but it's sometimes convenient. You can construct a simplicial scheme, a simplicial object in the category of schemes. How do you do it? You don't stop at morphisms. You take the entire nerve. So you take entire thing, it's called check nerve. You take the Fourier product of X0 with itself over X many times. And then from Xn, you have many maps. So we say that from X1, we have 2 maps to X0. But for X2, now we have 3 maps to X1, etc. So intuitively, you can think about Xn like tuples of composable morphisms, because this is what the Fourier product gives you. And then you have many projections. So you can erase one of the morphisms, so the last one, or you can take any adjacent two and compose them. So you get this big diagram, which together forms a simplicial scheme. And also you have maps upstairs because of the identity morphism. So you have maps upstairs. So there will be the degeneration, and downstairs will be the boundaries, and together you get a simplicial scheme. And of course, it may look completely useless because all the information is already encoded in this map. But okay, this map is not in the world of schemes, or even not of algebraic spaces. So if you want to go to the world of geometry, all the information is encoded here. So there is no reason to encode. So when you start with groupoid object, you can inflate it and get a simplicial scheme, and it doesn't give you any new information because all the information was there before. But it might be more convenient for bookkeeping because there's much more things to care about, but they're much more organized in that way. And at some point it will become relevant. Okay, so now when we understand what is a presentation of a groupoid by a scheme, we just can restate our theorem that any stack can have a representation by a scheme which will be essentially surjective. So meaning on the level of points. And again, we need some conditions either on X Gothic or on F. So is it okay? Any questions? And I'm out of water. Okay, so yeah, still.
So in the case when you have a quotient stack, so you mentioned that somehow you just base change sort of to quotient by GLN. Is that what you need to? Is that all you need to do, or you do something more complicated in that case?
It is all what I need to do. If you will take this proof is not very effective. Oh, it is effective, but not okay. Not good effective. So if you will go over this proof for quotient stack and you see what you do more complicated thing. But just because I want the proof to work in general and I don't care about the size of things.
But in the case of quotient stack, you just induce the JLN, right?
Yes, in case of quotient stack, this theorem is maybe not obvious but well known. So I learned it from Joseph. So for me, yes, and as for me, when I learned from Joseph at the beginning, okay, it was enough because I care only about quotient stacks. But it's always annoyed me. So now it's not annoying anymore because the same.
Rami, without linear stabilizers, does your theorem fail for periodic fields?
Yes. Yes, you can take elliptic curve and take, let G be elliptic curve, and then you take BG. So BG has no good presentation. Or it have good presentation over finite fields and other fields, but not over QP. So this is said, but it's just not true. So we cannot prove it. Okay. So yeah. So I know that maybe talking about proofs too much is not a good idea, but I think there are some instructive ideas in the proof, so I want to try to explain them. So the main idea of the proof is to break the theorem to two pieces. So the problem with the theorem is that it's global. We need to construct some X. So when you construct things, it's hard to construct them by pieces. So you maybe can construct it locally, but if you have open set and closed set, and you have something over open set and something over closed set, so to glue things together is bad. So instead of doing things locally, okay, so this is why we want to formulate a different theorem, which will be true for any presentation. So what I claim that for any presentation, maybe it's not onto, but Sasha, you asking something? No. So maybe it's not onto, but for any field F or field in our class, I want to be able to catch all the F points when I go to some field extension. So of course, by definition, I always can catch all the points when I go to some arbitrary field extension, or at least each point I can catch when I go to high enough. But I want to do something uniform. So for all fields, so I want to find for any stack and any presentation one number n, which will depend only on the presentation, and of course of the stack itself, such that it will fit all fields, or all fields in the class that we talked about. Yeah, but in all fields that we need. And for each such field, we will be able to go to extension of degree less than or equal to n and catch all the points. So of course, it doesn't mean that this map from x of e to x Gothic of e will be essentially surjective. But its essential image will catch all the f points. So if you want to catch the e points, you will have to go to another extension, again of degree n, to catch all of that points. Yeah, so again, we have the same conditions on x, Gothic, and f. Okay, so the advantage of this theorem is that it's amenable to stratification. Yeah, so again, we still constructed here something. We say that there exists a number n, but it's very easy to glue two integer numbers. If we have open set and closed set, then we take the maximum of two integer numbers and it will work for the maximum. So yeah, so when this theorem will be much easier to prove because we can break the stack to pieces. And now we want to use this theorem and to start with arbitrary representation of a stack X and upgrade it to get a good presentation, an onto presentation. And here is a construction, or not the construction itself, but what we want from the construction. So we start with some presentation. And let's say at the beginning, we have some fixed field extension. And now we want to upgrade our presentation from X to X Gothic to a new presentation, which is called Psi, from X prime to X Gothic, which maybe will not be onto, but it will be better. So before we had, so what does it mean better? So in this presentation, we'll catch more points. So we will take the image of what point this presentation catch, and we will want that it will catch all the points that for the previous representation we needed to go to E in order to catch them. Yes, it's okay.
Can I say, sorry, can I go back a second? And I wanted to ask you about the formulation of the theorem. The statement is that there's a good presentation when for it. You mean the same as that for every fixed f there is a good presentation.
No, much better.
Presentation which is good for all f's.
Yeah, you talk about the previous theorem. Yes, this theorem.
Well, I mean your main theorem,
yes,
that
main
you
theorem,
have several
yes.
formulations over here.
Yes. So yeah, there is presentation which will work for all f in the class, so not all of f at all. So either all perfect f or
that you're doing something for a specific f. You're kind of trying to.
Yeah, you're right. So yeah, this is why the study is not over. So this proposition only give us specific f and specific e. Yes, it's still not there, but it gives us a way to upgrade this part of the proposition. Give us a way to upgrade the presentation for specific field extension. And then the second part, the more offer part, we want the same thing that will catch all the given extensions of degree n. And the idea is that, okay, all the extensions in the world is not algebraic objects, but extensions of a given degree can be encapsulated in one algebraic geometric object. I will explain more about it. Okay, so, more about the proof, but the formulation is like this. It's given a representation, we can upgrade it and get a new representation that will catch all the field extension of a given degree. So it looks like the theorem and the proposition together are enough to to prove the theorem. This theorem and the proposition is enough to prove the previous theorem. And it's correct, but when we do this construction, we damage X a little bit. So this X prime, especially in the second case, but in fact, even in the first case, X prime might be not a scheme anymore. And here it's kind of annoying, yes, that we start with the representation by scheme, we improve it, it becomes better, but less scheme. But it's not a big deal, because what we actually do, so we have this upgrade, X prime, so we have better presentation. It will become, if we use the second part of the proposition, it will become onto if n is large enough, and large enough using the theorem here. So it's become onto, but it's not it's representation by algebraic space. Now algebraic space you can represent by a scheme, and then you upgrade this representation so it will become onto. Now we can ask, okay, maybe we have the same problem again, but not. If your original stack was algebraic space, or even if it was nice for some perspective, and all algebraic spaces are nice, then this upgrade does give you a scheme. So you have to do this procedure twice and you get a presentation. So now I only have two depths. Depth. Okay. And one is to prove the theorem, and the second is to explain how the construction actually works. I can continue? Or there are some questions? Okay, I continue. So the construction is based on the notion of internal home. So internal home is more or less equivalent to saying well restriction. So I don't know what name you're more familiar with, but anyhow. So it's basic construction from algebraic geometry. It's a priori not much more complicated than say fiber product, but but practically it's more complicated because it doesn't work so well. So if we have two schemes, we can consider the internal home between y and x. So a scheme structure on the home space between y and x. So how we define it? As usual, the simplest thing is to define the functors that it represents. So morphisms from S to morphisms from Y to X are the same like morphisms from Y times S to X. Okay, now we can ask whether or not it's represented by schema. And here is a problem that often not. So we need to ask something. First of all, we can do the same over a base. So if everything happens over some base scheme S, so we can do power over S, so it's standard. But we need something. So basically we need the Y to be very nice and very small. And you can see why, because okay, taking X squared, it's twice the dimension of X. So if Y is 2 points, then X squared is already larger than X. If Y is finite, X to the Y looks reasonable. But if Y is infinite, then X to Y looks unreasonable. So first thing that we want to ask is Y to be flat over S. If Y is not flat over X, then we need a deep problem, because then this functor, this is a presheaf, it's not a sheaf. So of course you can sheafify, but when you sheafify, you actually kill things. So it will not make sense, I think, to call it X to the Y afterwards. Or it will not be internal home, it will be something different. So you want Y to be flat over S. The second thing that you probably want to ask is Y to be proper over S. So this you don't really have to ask. So for example, if you do affine plane, and you can consider the internal home, or the homomorphism, automorphisms of a affine plane, or even a affine line, you can consider all the homomorphism. Not automorphism, but just homomorphism of a affine line into a affine line. You know what it is, it's polynomial, they're very nice, but it's not an algebraic variety, or it is a scheme, but it's somehow a very big one. Maybe it's even not a scheme, but an in scheme, but it's too big. So if you want something reasonable, you want Y to be proper. But even if Y is proper, this something you get something reasonable, like I don't know, automorphism of complete variety is reasonable, except that it might have many components. So it is finite dimensional, or at least locally finite dimensional, but it's still not something of finite type. So if you want to get something really nice, you want the morphisms to be finite, and then you expect to get a variety. Or except to get a scheme. So except of that, you probably not get in general scheme, but you get an algebraic space sometimes. And also, I did not find a reference for this for finite schemes. No, I did find, but I want everything to be a finite type, and in the reference it was not clear that it's a finite type. So if I want everything to be a finite type, I also will ask Y to be a tal. It's not something that I have to ask, but just in order the proof will look better. So let's Y to be a tal. So if Y is a tal, then indeed this power, this inner home, is always algebraic space. And moreover, if X from the beginning was quasi-projective, then this internal home is also representable by a scheme. Yes, so this is a standard statement, but I did not find it as is in the literature. We didn't find it as is in the literature, so we just reduce it from what we did find, which is very simple because it's mostly proven there. And moreover, if Y is a tal over S, this is something really intuitive, because over each point we just have finite set. So over each point we just have usual notion of X to the power of finite set, and then we have to glue these all things together in some not completely obvious way. So okay, this is rather simple. Now we can upgrade it. Instead of doing home between two schemes, we can do a home between two diagrams. We have two diagrams of the same shape, and then we do internal home between them. When I say internal, it's a little bit misleading because I mean home as a scheme. Yeah, we consider the space of all maps between two diagrams, but we consider it as a geometric object, as a scheme. And this immediately follows from proposition. We just take limit of the corresponding functors, yes, of corresponding schemes, and limit commute with unit embedding, so everything works. Somebody ask something? Oh, okay, I will read afterwards. Okay, so now we can state our main construction, how the construction actually works. So we start with a cover with a presentation x0 to x, and we want to upgrade it. So the first thing we do these towers, this nerve, this simplicial object that basically represents the groupoid. And then, so we want to upgrade it. We want to upgrade it to some specific map. So before we had field extension, but more generally, we have some metal map, S0 to S. And then we do this internal home between those two towers. So what actually happens here? What, not internal, what is the set theoretical home between those two towers? Those are exactly the same data. So they're exactly what you need to the information you need to give in order to get S point of the stack. So in order to get S point of the stack, you need to give S prime point of the stack together with some isomorphism and together with some coherence condition. So you basically need 3 levels, so 2 levels of information and another level of condition. But here I say, let's do arbitrary many levels. And the reason is that when you write it like this, it's much easier to say that you have a map such as the diagram is commutative. Otherwise, sorry, that you just have a map between 2 diagrams, morphism between 2 diagrams. So then I know how to do it on the level of internal home, just map between 2 diagrams. So at the beginning, we try to do it with a hands-on definition of stack, of descent data, sorry. And it was possible, but it was really ugly. And here, so we don't really need to do it for all n. We need to go at least 3 levels. Once we have 3 levels, and we have enough information, but you already in the 3rd level see that you have a little bit too much information. So why? Because not too much, but redundant information. So you want an object, S prime point of X Gothic. Then you want some isomorphisms, the gluing data. And then in the 3rd level, you a priori expected to have only conditions. But when you do it in this language of map between simplicial objects, you have kind of more data, which is completely redundant because it can be read from the previous data, but the fact that you have this data gives you the nice way to write what are the conditions. So yeah, the idea that you can take how many levels that you want and they all have the same price. You just say map between diagrams. It becomes easier saying map between diagrams than just to say map between, which just explain what is a descent data. And yes, for me, this was a point when I understood that this whole higher category language is not there to annoy me, it's there to help, yes, because even for one category, it's become hard to explain what is descent data, and this way all those machinery of simplicial complexes and later like other conditions was Khan and quasi categories, etc. They all encapsulate lots of combinatorial conditions, which become very complicated already in the rather low level of even one categories at some cases. Okay, so now we see that this main construction solves half of our problem. So if we start with, say, finite extension, separable extension, or everything is perfect, so let's take any extension, then when we upgrade our representation x and get x prime, it exactly will satisfy that condition star. So it will catch all the points that before we need to go to E. So this is half of our problem, but it's not all of our problem. Now we want to do it for all fields simultaneously. And for this, we have this nice construction. So this versatile étale cover. It's not universal. It's versatile in the case, in the sense that it's catch all the étale covers of degree up to n. It's not universal because it's catch each cover more than once, but we don't care. how we do it, we just take the space of all separable polynomials. Of separable, it just means that they are not coprime to their derivative, so have no double roots. Separable polynomials of degree less than or equal to n. This is a quasi-affine scheme. And this quasi-affine scheme have natural étale cover of it, which is this versal étale cover. For each polynomial, it defines as a subset of the line, and we just take it. Somebody asked what is the condition star. So okay, I will go upstairs a little bit because it's a good question. So this is a condition star that we catch that this upgraded presentation X prime catch everything that was caught before on the level of E. Now it's already catch it on the level of F. Yes, does it answer the question? Oh, I see that people are happy. So we need now to combine those two constructions. So the first construction was upgrade with respect to specific cover, and the second construction is this universal or versal étale cover. And how do we combine them? So we start with a scheme X with a presentation X that was over some base S. I don't write here the base, so you can assume it's spec Z. You base change to this versal UN, and then you do this construction with respect to this versal cover. And then the statement that it will do the job. It will catch all the points that otherwise we had to go to some extension of degree n. And you see that you may break the schematicity, so X prime is not a scheme anymore. It's might be an algebraic space because the internal home. But you also see that if X was nice enough, X Gothic was nice enough, for example, algebraic space, then all those these towers that you get, so you can cover it by a scheme, by a fine scheme if you want, and all the towers that you will get will be built of quasi-affine schemes, and quasi-affine are quasi-projective, and then what you will get after the upgrade will be still a scheme. So you see that if you do this procedure twice, you solve the theorem. And now I have only one depth is to prove this theorem about almost onto presentation, but I'm afraid I do not have time to pay this debt. So I just leave a slide and you can ask questions about it or anything else. This is it. Thank you very much. Dima, I don't hear you.
Yeah, so any questions?
Yes, I mean, maybe I didn't follow something, but so what happens? So this works for all F. Maybe I missed the point where F is varied.
Yes, because of this UN. So once you do it for this UN, it's a scheme. Yes, it's this scheme, but
okay,
it feels
okay.
like you can live over one of its points. Yes, because like spec Z is a most universal scheme in the world. Yes.
Yeah, cool. Thanks.
Rami, since we don't provide coffee, you can use another 5 minutes and tell us the last slide.
Okay, I would be very happy to. So you do have this. So we now have this theorem that we want to find n such that when we use all of field extension of degree less than or equal to n, we will catch all the points. And the main thing is that it's something which is very flexible. In particular, it's amenable to coverings, to stratifications. So now we want to do it by series of special cases. Start with some simple special cases and then go to the general case. So the first special case is a scheme. There's also something to prove here because of course, any scheme have a good presentation identity, but we want to prove that any presentation is almost good. And this is done by some Chevrolet-like argument, so it's rather simple. The next case is for algebraic space. Maybe before I need to say that all of this step is very important, because what does it give us? It says that now it's enough to show that there exists one nice cover. Because once you have one nice cover, any other cover, you can take the fiber product and just use the fact that for schemes everything will work well. So if you have one nice presentation, then all the presentations are nice. So now we can choose the presentation that we want to work with. And if we have algebraic space, we would rather choose very nice presentation. Any algebraic space can be written as a quotient of scheme by a Tal equivalence relation. So we choose this presentation, and then it's rather easy. So each time you have to do some n. So here n will be somehow some kind of degree. Here n will be the size of this Tal equivalence relation. Now you do BG. This is maybe the core of the theorem, and here we see the original idea, at least for linear groups, so the linear case of the embedding to GLN. So what we actually need is some control on the first homology. And in the linear group case, it comes from embedding to GLN and from Hilbert-90 theorem. And for general groups, but say finite fields, it comes from Lang theorem. That say if connected groups have no homologies, and non-connected group, you do have some control on the first homology, so you can catch it. Okay, this was a group scheme over a scheme. Now you can do group scheme over algebraic space, which follows from the previous step and the second step. Okay, now you have the case when X is a gerb. So what is a gerb? Gerb is a groupoid, sorry, is a stack, which locally looks like BG. Globally, it does not have to be BG, but you can, it's groupoid over some base S, and you can cover S locally, and locally it looks like BG. And okay, since this theorem is amenable to working locally, again, because working locally is even less harsh than going to stratifications, then you can do it for gerb. And the last step is general stack, and there is a very nice theorem that's saying that general stack can be stratified into gerb. So you know it for nstata, you know it for everything.
What is a gerb?
Gerb is a stack, say over a scheme or over algebraic space that locally on this algebraic space look like BG. So globally it doesn't have to be BG with 1G, but in each open a Tal cover, of course, or a Tal locally, of course, you have BG.
Thank you very much. Further questions, please?
Just thank you to Rami. It was a great talk. I enjoyed it a lot.
Thank you.
So there are some questions in the chat.
Oh, okay, I can try to see them.
I can sound them. First, what would be counterpart of this question in the setup of differentiable stacks?
So there, as far as I understand, there is no such issue because you can, like, you don't have this problem of field extensions. And maybe you can talk about maps between some nice manifolds, but then it really depends on the manifold. So if it's if it's contractible, then of course map between manifold to a like smooth stack is. I hope I understand correctly. Differential stacks, you mean stacks in the world of smooth manifolds?
Yeah, and Lie groupoids.
So if you have something which is a point, so it's a point in differential topology. Point is a point, and if you have something constructible, it's also okay. Then okay, then I have to think, yes, and then in general, not any presentation will be good, but maybe some stacks will possess good presentation because of some not Galo already, like some pi1 homologies, yes. But, yeah, I don't know, but naively there is no point because there's only one case of a point, but if you want to consider some other small manifolds for testing it, so it might be interesting. Other questions?
Yes, I have a question. What about Nash manifolds?
So one of the motivations, one of the applications was for Nash manifolds. For example, if you start with algebraic stack, it should be smooth. Then you can consider its R points. And then you expect to get a Nash manifold, but a priori you don't get a Nash manifold because R point might be very, very large. But if you choose a good presentation, then you do have a, not Nash manifold, sorry, Nash stack. Then you do get a Nash stack. So this give you, this is application of this theorem that R points of a smooth stack are Nash stack. Again, for Nash stacks, there should be no problem because point is just point and it's okay, it doesn't have covers.
Okay.
Other questions?
All right, so we reconvene in 8 minutes for Vladimir Berkovich's talk. So there was a question, what is a Nash stack? Nash manifolds are smooth semi-algebraic manifolds over the reals.
And for Nash stacks, so probably it's better to ask Yanis because he wrote a paper about them.
Yeah.
Sorry, what is the question?
The question was, what is a Nash stack? And
okay, maybe some other time. I mean, you can think of it as a groupoid in the category of Nash manifolds.
Yeah. Very good. So we continue in 7 minutes.
Сделаешь unmute, все.
Иван, ты меня слышишь?
Yes, Vladimir, we hear you. So are you ready? So I'm glad to present Vladimir Berkovich. He will tell us on Hodge theory for non-Archimedean analytic spaces.
Thank you very much. And so I'm probably here the only one who was not a student of Joseph and or his collaborator, close collaborator, at least among Russian-speaking speakers. But I, for the first time, approximately 50 years ago. And so not many people here can claim that. And I already knew at that time that Joseph and his fellow Gelfand student, Dima Kazhdan, were superstars mathematicians. And so I, in fact, met Joseph only many years later in Israel in '87, I think that. And in spite of the fact that I was not his student, in fact, I studied some of his major works and benefited a lot. So I'm very honored to talk here at this conference. Okay, and so I start my talk. First of all, I clarify things if somebody doesn't know that the word non-Archimedean usually is associated with periodic numbers. And so one might think that it's Hodge, periodic Hodge theory. Not, it's about classical Hodge theory. And the reason is that much earlier than the time when periodic numbers were discovered, in fact, there were already mathematicians used non-Archimedean fields. Namely, they used formal power series and the field of Laurent power series. And so it is the case over the field of complex numbers. And it is the case, it is a non-Archimedean field here. And so it was already used in several lectures at this conference. And let me start. I start with some prehistory. And so to give some motivation, let K be the fraction field of the ring of of convergent power series at 0 at the complex plane. And X, let X be a proper scheme over K. Then in that case, we can associate with X a complex analytic space over a small punctured disk in the punctured complex plane. And so it is, if the radius of this disk is small enough, then it is a topological covering. Vibration. And so this association, if T is a point of the punctured disk, and if we are given Q, non-negative integer Q, then one can consider cohomology groups of the fiber of this morphism of complex analytic spaces with coefficients in Z. And so one knows that it's a local system of finitely generated abelian groups, but not just finite, but groups which are provided with the mixed Hodge structure of mixed Hodge structures.
Can you just recall what is OC0?
It is the ring, local ring of convergent power series at 0 on the complex plane. C is the complex plane, 0 is 0. Okay, and so it's structured.
And D is open?
Yes, D is open. Usual Ds. And so I'll use this MHS in future, so mixed Hodge structures. And so one can associate with such a local system, also it is known, so-called limit mixed Hodge structure. In fact, on each of these groups, but since all of these groups are non-canonically isomorphic, there is a some group which is can be defined, and now I will recall the definition, which is denoted in such a way, which is non-canonically isomorphic to each of these groups. And so let me define this group. So let us again, so we have a complex analytic space of a D star. D star is a punched disk on the punched plane, and consider the universal covering of C star, which is given by the usual exponential function. And so let us consider the preimage of D star in this universal covering and the fiber product of the complexification of X with this inverse image. Then we can define the following group. So in fact, since the preimage of the punched disk is a simply connected space, it's already the local system is trivial. So we can consider the following. So the group I was talking about is the following. It's just inductive limit over small disks, small open disk at 0, with center at 0 of the cohomology groups of those spaces. And so it is this group which is provided with limit Hodge structure. So there is a theory, mixed Hodge structure. And I want to mention some result I proved some years ago. I gave a description of the weight 0 part of this group in terms of non-Archimedean analytic geometry. Not this group, but cohomology group with weight monodromy filtration exists on rational cohomology group. And so now I recall the fact. And so our field K is a discrete valued field. It is not complete, and so we can consider its completion. And so it's a non-Archimedean field. If we fix a real valued valuation, we get a non-Archimedean field. And in fact, this field is isomorphic to the field of formal power series, Laurent power series. And in fact, I always, when I talk about complex plane, I assume that I fix coordinate function Z. And so this field is canonically isomorphic to the field of Laurent power series. And so in this case, we can associate with X a non-Archimedean analytic space, which is, first of all, we lift X to this completion and consider the non-Archimedean analytification. And so it's a proper K hat analytic space. And also let us consider like a lift of this space to the completion of algebraic closure of this field. And so I lift X to the completion of algebraic closure of this field, which is a non-Archimedean field, already non-discrete. And so its analytification, it's proper, but this time over bigger non-Archimedean field. And the result I wanted to mention is that there is a canonical isomorphism between cohomology groups of the underlying topological space of this analytic space with coefficients in Q and the weight 0 part of this complex analytic object. Okay, and so why I denote the underlying topological space, because for non-Archimedean analytic spaces, there is also much stronger étale topology, étale cohomology group. And so if I don't want to mix them, I denote this underlying topological space. Okay, and so this fact, in fact, I already at that time, I like conjectured for myself that the right-hand side, the group of these Q-dimensional cohomology groups, group in fact lives completely in the
I stopped hearing anything.
what?
I didn't hear anything for several seconds. Maybe it's only me, I don't know.
I got a message that there is a problem with internet connection, probably. Okay.
Can you for a second go back to the previous slide?
Yes.
So I'm a little bit confused about the right-hand side. So just the notation, X bar, K. Oh, this is the little k is the residue field, right?
Where I do not see little k.
Or is it not k? I mean, can I just say what is written? I mean, you have this isomorphism. Oh, the right-hand side is the same as before, so it's the analytic thing.
Yes, yes.
Okay.
And left-hand side is a rational cohomology group, singular cohomology group of the underlying topological space of this non-Archimedean analytic space.
Okay.
No, non-Archimedean over K hat?
Over a completion of the algebraic closure of K. It's
you need a bar.
What?
You need a bar.
You see, now I should admit that I denote algebraic closure in such a way. A, not standard notation K bar, A. A stands for algebraic closure. And it's a completion of algebraic closure.
In the left-hand side.
A bar.
What?
You need a bar on the left. Or maybe.
Yes, yes. Wait. Thank you very much. Thank you very much. Yes, 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 yes. I'm sorry. Thank you very much. I did not notice this. Okay.
What are your assumptions on X?
It is a proper scheme. It's not necessarily smooth. It's a proper scheme.
Thank you.
Okay. Now I already can explain very briefly what can I do, and after that I'll give details. So briefly, so the statement. One can define for any compact K hat analytic space X. It's already object of a non-Archimedean geometry. And for any K, Q, which is non-negative integer, one can define a certain group, HQ, X bar, Z, which is denoted in this way. And so it is a finitely generated group, abelian group, with provided with a quasi-unipotent action of the fundamental group of the patched complex plane and functorial in X. Okay. And the next, if X is proper. And so in non-Archimedean geometry, compactness doesn't imply properness. Just in non-Archimedean geometry, the class of compact analytic space is much bigger than the class of proper analytic spaces. And so if X is proper, it is provided with a mixed code structure, functorial in X, and such that if X is the previous, the analytification of the scheme as in the previous slide for X proper over this field, K, it is this group just coincides with the previous group, HQ, X, H, R, Z. Okay, it's already essentially, I explained the main result of this talk, but there are some curious details, and so I'm going to explain. Okay, so but essentially everything, it is a result. And so this means that this group, which is this group, is completely comes from non-Archimedean geometry. In fact, there is no similar description of the same type of weight zero part. It's more complicated, even I do not know, but, and moreover, all proper analytic spaces are cohomology, this integral Ital cohomology groups are provided with mixed Hodge structure. Okay, and so, but let me, before going further, I recall that the construction, so now I want to explain in the construction of the limit mixed Hodge structure set in depends, the classical construction depends on the choice of a non-zero element of the one-dimensional vector space over C. So M0 is just the maximal ideal of that ring of convergent power series. And so, in fact, the Weidmann-Andromi filtration does not depend, but Hodge filtration does depend. Even it is already mentioned in the talk by Deligne in 1970 in Nice. And so when he suggested that there exists such a structure, it was shown later. And so in construction, and I want to also to give some framework when such dependence is very natural. So it is also included. Okay, and so let me give more details about everything. So first of all, I start with like an abstract field, non-Archimedean field, which is isomorphic non-canonically to the previous field. So K is a non-Archimedean field. So I introduce this like with its property. With discrete valuation, so this means that complete with this, with respect to discrete valuation. And so I recall or introduced standard notations. And so K naught is the ring of integers in non-Archimedean geometry, like unit ball, it's a subring. And in fact, it is a local ring and it has maximal ideal, which is in fact principal ideal. It is denoted in such a way. And I'll use this notation. And also the quotient ring, which is a field, it's called the residue field of K. And in fact now, I'm sorry, here K, just already, calligraphic K is reserved for the previous field. And so I assume that the ring of integers contains the field of complex numbers, which maps isomorphically onto the residue field. And in fact, example of such a field, of course, it's our previous field, which is the field of formal round power series. And in fact, if var pi is a generator of the maximal ideal, then one can just construct an isomorphism from this calligraphic K hat to K, which takes Z to var pi. Okay, but it's convenient just to start from an abstract field. Now I want to introduce, associate with this field, the following complex analytic space. The notation is maybe looks slightly crazy. It is the complex analytic space which is in fact, its points are, let me even at the beginning complex, it's just the quotient of the maximal ideal by the square of the maximal ideal. You remember it's a function equal to 0 by squares of such functions. And so here, let us consider, and so in fact, it is a one-dimensional vector space over C. And so it's like, let us consider it as a complex analytic space. And so, but in fact, the main subject is its punctured space. It's just this space minus 0. So its points are this.
Volodya?
Yes.
Do you assume the field to be complete?
Yes, yes, of course. I'm sorry if it's not clear. And so non-Archimedean field, it's always complete. It is assumed by default. Otherwise, it's in this sense, not just variation, but complete. Yes, of course. Yes. Okay. Now, this space, in fact, I do not. I want to say that, in fact, in my presentation, I do not give much definitions, only I give some logical picture of objects. And so one can construct, in fact, for any point of this, I'll explain, one can associate with any point of this space, which is a principal homogeneous space, by the way, principal homogeneous space for C star. So one can associate with any point of this space. And so it's like generator of the maximal ideal, but by modulo square of the maximal ideal, one can associate a universal covering. I explained something philosophically that this space, it's like classifying space of universal coverings of this space, of the space. Or I forgot to mention, and so the reason, first of all, before I started introducing objects, the reason that construction depends on the choice of a non-zero element of this quotient is, first of all, that in the construction of the group, you remember, I considered universal covering of C star, but there are many universal coverings of C star. Of course, all of them are isomorphic, but there are many. And so each choice, each universal covering gives its own group. And so it's, in fact, we get in such a way some functor from groupoid to universal coverings to abelian groups. And so, but there is, of course, there is a classifying space of universal coverings. And so just, I want to say that one can associate with any points of this space, universal covering of this space. Covering. And also one can associate with this space an algebraic closure. I do not give a definition, it's not difficult, it's very quite easy. Algebraic closure, just to explain closure of K. One can construct that it is, these are functors. These are functors on the fundamental groupoid of this space. So Rami gave definition of groupoid, but it's very fundamental groupoid, which is denoted in this way. Of course, it's a groupoid. And so points are objects of this groupoid are points of this space, and morphisms are homotopy types of passes from one point to another. We will be back to this groupoid slightly later, but one can construct such functors. And so, the first functor, in a sense, is a classifying space of universal covering. Okay, let us continue. Or maybe I look to my notes and I give some, because it will be important slightly later. And so this fundamental groupoid, as I explained, its objects are points of this space. Now, morphisms are homotopy classes, but in fact, one can give easily more concrete description of this groupoid in this case. So if you have 2 points, var pi 1, var pi 2, then one can identify the set of morphisms between var pi 1 to var pi 2 with the set of complex numbers such that exponent of gamma equals to var pi 1 over var pi 2. And so this fraction is a well-defined complex number, and so we just fix a logarithm of this complex number. And if we have such a gamma, one can associate to it the following path to this space. It takes t to exponent minus t gamma, if we have gamma, times var pi 1. And so it is a path which we present, and so it's convenient in future for several more slides, and so we'll use it. Okay, and so the functor which takes var pi to the algebraic closure is a functor, and so is a functor from this groupoid. From this groupoid to the étale fundamental groupoid of the field. So its objects are algebraic closures of the field. And so it defines a functor from the category of étale sheaves on the spectrum of K. So discrete modules of the Galois group, but étale sheaves to the category of locally constant sheaves on this space. Namely, if you have such a sheaf, I'll denote, we associate to it the following. And so we associate with very point var pi the value of this sheaf on the algebraic closure of K, this, which is associated with var pi. And so it defines, it's a functor on groupoid, and so we associate a sheaf which is also denoted in the same way. And now already I'll give an example. When X is a K analytic space, and let us define associate with X the following analytic space of the completion of this field. So this algebraic closure is not complete. And so it's a K hat analytic space. And so if you have a étale sheaf like here from on the spectrum of K, one can consider on the spectrum of K. So if you also have a non-negative integer q, one can consider the following correspondence. Étale cohomology groups of this space, with coefficients in lambda. No, even in fact, in the value of lambda at this algebraic closure. And so in such a way, we get a local system, which is denoted, it's a local system, which is denoted in such a way. Local system. On this space. And in fact, the object I now introduce will be of this same type. Okay. Now I formulate the first main result. One can construct. It's not the max, I formulated not in the maximal generality I can do, but it's convenient to restrict for any compact all analytic space I consider like strictly analytically for those who knows what it is. Space X, and for any non-negative integer Q, a functor from the category of abelian locally constant shifts on this space to itself, which is denoted in the following way. And so if you have lambda, it takes lambda to locally constant shift, which is denoted in this way. So what are properties of this functor? And so it's a locally constant shift on this space, which is non-canonically isomorphic to the punched complex plane. So such that, first of all, if lambda is finite étale on the spectrum of K, then in fact we do not get anything new. It's just étale cohomology groups of this space, which are well defined. And so I also maybe tell that this functor, it's a notation suggestive. It's a not high direct images of certain left exact functor. That's not true. It's just such objects are introduced and they possess many usual properties of cohomology groups, but they are not high direct images, at least at the moment. I cannot. And so now, in fact, the most interesting object and everything can be expressed in terms of étale cohomology with coefficients in Z. And so it is a quasi-unipotent local system of a finitely generated abelian group. Okay, and third property, if X is the analytification of a proper scheme over that field, proper scheme over K. I recall that calligraphic K is a fraction field of the ring of convergent power series, and so as I told that we always fix, and so the coordinate function, a coordinate function on the complex plane is fixed. Now, then this group is, and so what, it's a local system. And so this coordinate function on the complex plane defines an element of the quotient, or a point on the associate this analytic space. And its stock at this point is precisely the group we were talking about in the beginning. Okay, and so it's what about integral at all cohomology groups. I just want to mention that this first fact implies that for any prime L, if we tensor this group with the L, we get analytic cohomology groups in terms of étale analytic cohomology groups, which are well defined and are known to define. Okay, let us continue. Now, in the story, there is a second ingredient. In this.
Volodya, could you please show the previous slide?
Yes, yes, of course.
So just an administrative request, please give us 5 seconds at the end of every slide to read the last sentence.
Okay.
Thank you.
Yeah, I continue. Now, there is also another ingredient of the whole story. So we know, because we are going to the direction of Hodge theory, the RAM cohomology. Okay, if and so X is a K-analytic space, if it is so-called, I call Rig smooth. And so this means that it is smooth in the sense of rigid analytic geometry. So my notion of smoothness is more restrictive. And so, okay. And so one can define cohomology groups, the RAM cohomology groups of X over K, which are just hypercohomology groups of the RAM complex. But, and these groups are provided with Gauss-Manning connection. Okay, let me, otherwise. And in fact, omega 1 of K is a one-dimensional vector space over K. And so now what can I do with these objects? First of all, if X is compact, then first of all, these groups are finite, have finite dimension. It's non-evident. And in fact, there is a very canonical lattice, which is denoted in this group. And so it's a vector space of finite dimension over K, but in fact, it contains a lattice, which is denoted in this way. And which is also provided with a lattice, plus Gauss-Manning connection. Which is also works in the in similar way, but it goes to so-called omega 1 K naught. Now I'll explain. Because in fact, it's so-called, it's a free module of rank 1 over K naught. It's a logarithmic, the module of logarithmic differentials. And so we consider K naught as a logarithmic scheme with a canonical and so logarithmic scheme, which is defined by the monoid of non-zero element of K naught. And so it defines logarithmic structure on the spectrum of K naught. And so this group, in fact, it's generated by the logarithmic differential of any generator of K naught. And so var pi generator of the maximal ideal. It is one free module of. And second fact I want to mention, one can extend in a smart way the above to a functor. Not necessarily Rig smooth analytic spaces, to functor on compact analytic spaces, on the category of compact K analytic spaces. Strictly K analytic spaces, in fact, I I should put, and so which takes X to the RAM cohomology group. And so one can imagine how can one do. And so this, and so one can reduce everything to weak smooth analytic spaces due to, one can, instead of X, consider its property the covering by weak smooth analytic spaces, which exist by Michael Semkin result. And so after this, one can do some manipulation and one gets these groups. Okay, let us continue. And so I, in Hodge, yes. Should I?
Yeah.
Yes. And so this means that it is a free module of finite rank over K naught. This, I mean that I show this is a free module of finite rank over K naught. And it is provided with a connection of the same time like here to tensor product with logarithmic differential of K naught. Okay, there is such an object. Let me, now I hope I can continue. But now I just, in Hodge theory, the most important part of this group, in fact, I can introduce also, don't ask me about this notation, because instead of one can put any integer, even infinity. And so it's, let us consider the quotient of this group, the RAM cohomology groups. And so now X is a compact analytic space. And so let us consider by sublattice, which is generated by the maximal ideal of K. And then, in fact, instead of connection, there is an operator which acts on this space, which is so-called residue of the connection. And so its space is a finitely dimensional C-vector space. It's a quotient, and there is an operator which on this space, it's so-called residue of the connection, of the previous connection. This, okay, now definition. An intermediate step. A distinguished drum structure on this space is a triple. So H, which is HZ, E alpha, where, and so HZ is a local system of finitely generated abelian group. On this space. Second, E, finitely generated, finitely dimensional C-vector space. And this provided with an operator on itself such that its eigenvalues lie in Q intersected with the unit interval. And so it's a rational number which is at least 0, which is strictly less than 1. So something appeals to something. And third, alpha is an isomorphism of vector bundles. This connection. And so what are vector bundles? It's V tensor to the structural sheaf of this space, which AZ. And here on the right-hand side, we tensor the same structural sheaf over C with E. Now, the connection on the left-hand side is clear. It's just generated by connection on the structural sheaf, the differential. And the connection on the right-hand side takes into account this operator, namely, if X is in E, then connection on X is just delta of X times d logarithm of Z. And so there is a canonical logarithmic differential on it's dt over t, in fact. On the space is isomorphic to C star, non-canonically up to multiplication by non-zero complex number. And so it is an isomorphism of vector bundles with connection. But in fact, the vector bundle on the right-hand side, all fibers of these vector bundles are the same. It is a space E. And so this, this isomorphism induces for any, in fact, point of this space, just isomorphism between H, the stock of this local system, with the space E. And so at each point there is such an isomorphism. And now what is important, now I come back to the same groupoid. One can show it's not difficult, simple fact, but it's important that for any gamma from a path from one point to another, omega 1 to omega 2, I recall that it's a complex number whose exponent is the quotient. Yes, there is a commutative diagram. And so H z omega 1, H z omega 2. And so in fact, it's a parallel transport along this path. And so to each such gamma, one can associate a path. I explain. Now we have alpha omega 1 to E. We have alpha, the homomorphism omega 2 to E. And so what is here? It's exponent of minus gamma times delta. It is the operator by an exponent of this operator. It's also, I hope, gives some, appeals to something. For example, if gamma is a loop around a point, then gamma equals to, we should take gamma equals to 2 pi I. And we gave a formula, then such a loop is just corresponds to exponent minus 2 pi I delta. It's like delta is residue of connection. So it's something familiar, very familiar. Theorem. So the first theorem, maybe let's, for any compact analytic space, K analytic space, and for any Q non-negative, one can associate a distinguished Avraham structure on the quotient HQ X bar Z, HQ Avraham X over K not 1 alpha. Okay, it's an important ingredient in for Hodge structure. Now, and it is functorial in X. Okay, now we come to already to some notion, definition. A distinguished mixed Hodge structure on this space is a tuple. So HZ, HQ omega. It's also like E omega F, where first of all, HZ is the triple HZ W, oh, I'm sorry, HZ E alpha is a distinguished Ram structure. And so this part HZ E alpha is a distinguished Ram structure on this space, provided with a finite increase in filtration W on the rational part of this Ram structure. And so instead of integral local system, we consider rational, but everything else is the same by the Ram substructure. In particular, it is a filtration on rational local system, but also it is the same W here, I already explained, which is preserved by the operator delta. Delta also is present here. Second, F is a finite decrease in filtration. On E by C vector subspaces. Such that, here it's in such that if delta, if we consider additive Jordan decomposition of our operator delta, and so this is the Ram structure, and so it contains in the definition operator delta on this vector space E. And so if is an additive Jordan decomposition, then A, we consider filtration. In fact, it follows from the, okay, let me continue. And so the filtration W and F, and so W is a Bateman-Avraham filtration, and B, the behavior of Hodge filtration. And so Hodge filtration is preserved by the semi-simple part of this operator, but nilpotent part behaves in the way indicated by Griffiths, and so it's a Griffiths transversality. Okay, and the last property, for any point var pi in the space, the triple, the stock, oh, sorry, something. HZ, the stock of our local system at var pi, filtration, so, and FW, is a classical mixed Hodge structure, is a mixed Hodge structure. So I'll explain what it is. And so W var pi is just filtration induced by our filtration W here on the stock of this filtration, and FW, I explain. And so you remember that we have an isomorphism from HC omega to E, and so it's just the preimage of this filtration. Preimage of this filtration F, this stock, okay. And so it's a classical mixed Hodge. In fact, it's a very particular case of a variation of mixed Hodge structures. Okay, we still have 5 minutes, I can formulate the last theorem too. For any proper K analytic space, so it's important proper. I believe that one can extend everything for arbitrary, but at least compact. One can associate with it the Hodge structure, let me denote in such a way. Which is denoted such a way, which is a tuple. So constructed HQ X bar Z, HQ X bar Q, W, the RAM homology group of X over K node 1, W, F, and some isomorphism alpha, a distinguished RAM structure. The RAM so that, first of all, it's functorial in X, again, in the theory of limit mixed Hodge structure starts from semi-stable proper schemes of the link of convergent power series and so on. And to extend everything to arbitrary schemes, I just consider everything under finite extension. So for any finite extension chi prime over K, there is a canonical isomorphism. And so one can now I write down okay, I will explain. And so K prime is a finite extension. X prime is just lift of X to this finite extension. And also this space is associated space to this finite extension. In fact, I didn't define here the left-hand side. It's non-evident. The only part of the left-hand side which is clear, what is the lift of distinguished, I wrote the RAM structure, it's distinguished mixed Hodge structure. Mixed Hodge structure. It's not the RAM structure, it's mixed Hodge structure. And it's not evident how to lift this C vector space, but there is a procedure. And the third property, if X is curly X analytification of a proper scheme, proper over calligraphic K, then again, we consider X over K not 1, the stock of our variation of Hodge structures at the point Z, which corresponds to the fixed coordinate function of the complex plane, it is canonically isomorphic to the group X, H bar Z, provided with a mixed Hodge limit structure. Okay, it's a main result. It's the main result. I have 1 minute. I want to now again maybe to emphasize again that in fact this property, this commutative diagram you see this commutative diagram, it precisely tells how everything changes under if we consider a different point. And so we should also consider a path from one point to another, and so everything changes in such a way. And so since weight monodromy filtration is a filtration of this drum structure, and so it changes accordingly. But Hodge filtration, it's already something, it's just changes in this way. And so it is not, it really depends on the point. In a sense, weight monodromy filtration does depend on the point, but Hodge filtration depends on the point. That's all I finished. And so I think that I am in time. I finished in time.
Thank you. Questions?
Yes, I have a question.
Yes.
So you define a Talca homology with coefficient and Z.
Yes.
So if you do it in algebraic situation, then it is not very good object.
What do you mean?
No, a Talca homology with coefficient and Z, it is, you can define a Talca homology with coefficient in ZL, but not in Z.
No,
but in your situation, it is well defined, yes?
Yes, yes, yes. No, it's an ideal situation. You because this cohomology give rise to all L-adic cohomology. And
yes,
cohomology, it's an ideal situation. It's like in the critical situation. If, by the way, if this we start from, for example, a proper scheme over C, we can lift it to this field.
Yes.
So we do not get anything new. It's a classical theory.
Yes, no, that
includes. Yes.
Okay, no, I understood. So you can get in this way. You can get cohomology with coefficient at Z.
In Z, yes.
Okay. Okay. This was my question.
Yes. Yes. It is a. And of course, Galois group doesn't act on it. Like Galois group acts on L-adic cohomology, but it doesn't act on this cohomology. Only part of this group acts.
Yes, no, I understand. Yes. Okay.
More questions? Okay, let's thank speaker again. And we meet in 13 minutes.
13 minutes. What should I do?
You press stop sharing.
Yes, yes. Thank you. Stop sharing.
And maybe, Andre, you can help me now.
Yeah. So, where is your?
To Dima.
Yes. Peter, I have your slides, but it will be more convenient if you put them through screen sharing. Then you will be able to control and to pass to the next slide.
Okay. Well, firstly, I can try to do that if you. So, do I do share screen?
First of all, you open it in PDF reader as you.
Yeah, that I've done. Okay.
Now you push share screen.
Okay.
In the list, you find.
Can you see that now?
Yeah, perfect. That's it.
Okay, I can control this. Do you see my little? If I use this.
Yes. Yes.
Okay, perfect. Thank you.
Okay.
So then we set.
Yes.
Okay, thank you.
Okay.
Okay.
So we meet in 10 minutes, and I also shared your slides in the chat.
Okay, thanks.
And they also appear on the homepage.
All right.
So see you in 10 minutes.
saw the cake.
Okay. So before the last lecture, I just want to remind you that after the lecture, you'll have a 10 minutes break. Then you'll take a group photo. And then immediately after the group photo, we will have this Zoom dinner. Everybody invited. And then as this conference, usual conference dinner, we encourage people to talk, to ask, to talk whatever they decide to talk. And maybe people will ask speakers or other way around about mathematics or something else. So we will leave this Zoom open for some time, and we hope that we'll some compensation of this strange situation. Okay, so we have the last speaker, Peter Sarnak from Princeton. So Peter, please.
Yeah, thank you. It's a great honor and a pleasure to be talking to celebrate Joseph's 75th birthday. Before I start here, I guess it's kind of customary if I'm the last speaker to acknowledge a great effort by Dima and Andre and Hani Naor in arranging this meeting. Under such circumstances, it's turned out to be, I think, much bigger than they had planned originally. The attendance from the numbers that I've been seeing is quite striking. So I think you've started something new here. And I think it probably is a great, it owes itself to Joseph. I think Joseph has impacted many of us, as I'll explain here a little bit. So anyway, let me thank the organizers for a tremendous effort. I can't control, but maybe at the end.
Thank you, Peter.
Yeah.
And thank you for all the participants and speakers.
It's really remarkable. All right, I'm going to talk about something very concrete. Erez Lapid said that Joseph was involved with the computer science people at the Weizmann Institute on very practical stuff, and that whatever Joseph does is very practical. And in fact, my co-worker is a young applied physicist, actually, who asked some questions, and I'll explain the theory. A very concrete kind of engineering problem, but central to things that I've been interested in over the years. So this is all joint work with Alicia Koller. She's my colleague Janos Koller's daughter. All right. So let me, before I start, I want to spend a few minutes explaining my relationship to Joseph, as everybody else has. So in 1987, we both spent a sabbatical in Jerusalem. It was a fantastic year organized by Steve Gilbert and Ilya Piatetsky-Shapiro, and many people came and left for shorter periods. But Joseph and I were there the whole period, and it was an opportunity for me to really be impacted by Joseph and the way he thinks. Of course, I knew him because of his early work with Sergei Gelfand on the meromorphic continuation of P to the minus S, a problem of that the older Gelfand had raised. The first solution used the resolution of singularities of Hironaka. Atiyah seemed to discover that proof maybe 2 years later, according to my understanding, and he said, who are these two other people who found the solution? Anyway, this led Joseph to the theory of D modules to give a second solution, and you're probably all familiar with that. But his way of thinking, which is just to understand mathematics rather than anything else, he just wanted to understand things, led to that and many other things. I want to say something about his proof of the meromorphic continuation of Eisenstein series, which was something that we discussed there already, and which is something that I think he came up with in the 1980s, and actually even up until today. We all say great things about Joseph, and I will as we continue here, but he does have this weakness of not writing things up. And it has caused a lot of problems for people who want to see details, probably because he always wants to perfect it. And in the case of the analytic continuation of Eisenstein series, that is certainly the case. I've been waiting for something for 40 years, 35 years, and it was delivered recently in a joint paper with Lapid. Lapid gave a talk about it last week. Let me say a few words about the historical comments about this, because I think the history is a little confused. So, of course, Selberg was the first to develop the meromorphic continuation of Eisenstein series in the upper half plane. I think Siegel may have raised the problem, and Selberg found a way of doing so. And that method works in rank 1, real rank 1, quite generally. And it was Langlands, on seeing that, developed the theory in general to meromorphically continue Eisenstein series for general groups. This is very important and led him, as you all know, to the theory of Euler products and to functoriality. So on interpreting what he'd done. But the proof in general is extremely complicated, as it's done in all treatments, starting with Langland's Springer lecture notes book, where you first analytically continue when you have a cusp form on the levy. You follow, his proof uses several complex variables in general, but it follows Selberg's original proof, at least in the style of meromorphically continuing up to a unitary axis and then using functional equations. Harishchandra wrote up the sort of first 6 chapters of Langland's. The real difficult part there that I think you see at the end of Langland's book is where he wants to analytically continue when you're inducing from anything on the levy, any residual, for example, and he only recovers that after the spectral decomposition. Now, you could argue that you need the spectral decomposition anyway, because the trace formula is so important. But in terms of analytic continuation of Eisenstein series, this is a little unsatisfactory, because you should be able to meromorphically continue the Eisenstein series just by themselves, and it's a very deep process. Selberg in '66 found a second proof based on principle of uniqueness, which he never showed to many people. I think he showed it to Harishchandra, and he started lecturing about it in the 70s and maybe early 80s with just general outlines. And it was written up by Paul Cohen and myself, and Wong wrote an account, but it became clear that Selberg had unfortunately maybe overlooked some point. You can look at his collected works. He repeats this there's an error there. It's possible that you can fix it some other way, but the uniqueness principle seems, at least in the Selberg L2 argument, only to work in the case that you're inducing from a cuspidal on the levy. In that case, it's a beautiful and brilliant argument, and essentially Joseph rediscovered it without any knowledge of this in the early 80s. But Joseph had a variation on this, which has become kind of crystal clear in this recent paper. So I'm maybe the only one talking about Joseph's most recent preprint. Let's get up to date here. In this joint paper with Erez, there's some very important variations on the uniqueness principle, which allows them to prove this meromorphic continuation where you have anything of moderate growth on the levy, and without having to go through recovering residues. And this is extremely important. It's conceptually beautiful. It's typical Joseph. And I'm delighted to finally see the details. I know Armand Borel was waiting for these details for many years. Unfortunately, never got to see them. Joseph had lectured around this in somewhat different ways. Maybe at the end of my lecture, he can say some comments. Anyway, that's one tremendous achievement by Joseph. In 1987, when we were in Jerusalem, Joseph showed me an idea that he had even from Russia with Kazhdan, a very elementary and ingenious idea to try give bounds towards Selberg eigenvalue conjecture, which is close to what I'll be talking about today. And it used a property of the dimensions, complex representations of Chevrolet groups of G's, let's think of SL2 of a finite field FP. Either the representation is one-dimensional. These groups are very close to being simple. So the representations, the irreducibles, are either one-dimensional or they jump tremendously large. In other words, the smallest representation is at least a power of the size of the group. So it's the order of the group to some non-trivial positive power independent of P. And that feature means that if there's a bad eigenvalue in some setup, then it must occur with high multiplicity. And it was a beautiful idea of theirs to try use that to give a non-trivial lower bound, a spectral gap, which is in the title of my lecture. At the time, a number of us tried to make it rigorous, carry this out. They didn't quite, or at least Joseph, and I think I've spoken to David as well, weren't quite able to make this work. Bob Brooks made a serious effort to try and make it completed. But anyway, for a while it wasn't clear, but eventually Xu and I found a variation, relaxing certain conditions, and found that you can make this work, and it's a soft proof, and it extends to combinatorial settings. And there is a very elaborate theory today of expansion in thin matrix groups, as I call it, which comes in three parts. There's a sort of an opening where you make expansion by ideas of Helfgott, generalized by Tau, Green, Brouillard, others. There's a middle game due to Bergen and Gumbard, and there's an end game. And the end game is always this old idea of Kazhdan and Bernstein, and I always give credit to them. It's a marvelous idea, and the idea now has become standard in the group theory, combinatorial group theory world, but they, of course, don't have the right history. Anyway, that's another typical thing of Bernstein's insight, conceptual insights. I once, more recently, I think it was Gromov's 60th birthday in Israel, I gave a lecture on estimating coefficients, solving some old problem of Selberg by complexifying some complex manifold into tube domains. And Joseph immediately came up to me after, actually, it was quite interesting. Both Bergen and Joseph came up to me immediately after the lecture, wanting to explain to me how they could do things much easier. Both actually had a very good idea. And this led to the starting point of Andrei Reznikov and Bernstein's work first on this complexification and later on using multiplicity one in ingenious ways and variation of test vectors, which has become the standard or a standard tool in some general subconvex estimates and estimating periods in the way that Akshay was talking about. And this series of papers by Andrei and Joseph is very influential. Of course, there are many, many other things, but there's one thing I've learned over the years. Joseph's a very quiet guy, but if he ever has something to say, you should shut up, listen. It's always gold. Whatever he says is gold. He'll only say when he's explained to you clearly what you haven't understood. All right, with that, let me turn to my lecture. So I'm going to talk about something very concrete. I will try to put it in a little more general context so that maybe some of you who are interested in symmetric spaces rather than just some combinatorial problem like this might then see the connection. So everything I'll talk about, the set X is the set of all finite, three regular connected graphs. I drew a little one over there, but I'm interested in these when they get extremely large. And this one is planar. And in since this problem is going to be of some applied nature, when people build certain networks in some of these kind of settings, especially the one that Carla is interested in, planar is a very important input, and that makes a very serious restriction in what we'll be asking here. Anyway, I'll set it up first in general, and I will discuss when we planar, we'll say planar. So X is a set, it's a finite, infinite set of, for each, the number of vertices will always be the size of the graph. It's a multiple of 6, and the size will be going to infinity. So there are infinitely many of these. And the thing we're interested in is the spectrum of the adjacency matrix, or I like to think of it as a Laplacian because that's the way I can connect it with things that I'm most familiar with. Just to be concrete, the operator, oh, I see I can point here. Does everybody see this thing? Yeah. If I put that thing, you see it. Okay. So the adjacency operator applied to a function on the vertices is that you sum the nearest neighbors, f of y. So it's not the Laplacian, but it's up to a shift in this regular case, a relative of Laplacian. The standard inner product on the vertices renders this operator self-adjoint. So there's no fancy spectral theory here. The issue is the engineering problem of trying to understand what the spectrum could be when this graph gets extremely large. So it's very easy to see from the definition that the spectrum is contained in -3, 3. So everything I'll be talking about will be contained in this interval -3, 3. 3 is a simple eigenvalue because the graph is connected. So it's very easy to see that. That's just the maximum principal argument. So 3 is simple. The rest of the spectrum will be between -3 and 3, 3 omitted. And -3 is an eigenvalue if and only if the graph can be broken up into 2 vertices so that all the edges go between the 2 disjoint set of vertices, what is called a bipartite graph. So these are the trivial remarks. And the question we want to ask, and I'll put it in context in a second, is if the graph gets very large, what gaps can we create in the spectrum? All right. Yeah. Yeah, please feel free to ask questions.
If negative
and,
3
I
is
see that Avi is, he likes to ask questions. Go ahead.
If
there's no derived stuff here, so I don't have to answer hard questions. Yeah.
So if -3 is an eigenvalue, it's still it's simple or not necessarily?
Yeah, it's simple. Must be simple. Right, correct. Because the graph's connected.
But also -3, yes.
If -3 is an eigenvalue, the graph is bipartite and the spectrum is symmetric about the origin, and 3 is simple and -3 is simple. All right, so the starting point of this, which was the thing that I was thinking about quite a lot in 1987, because I'd been working with Alex Lubotsky, just by the way. One thing that Joseph and I learned in 1987 was that if you go visit Jerusalem, then you will be giving a course. And since we were there for the year, we were instructed by Lubotsky each to give a course. And that was a good way for me to learn a lot. Joseph gave lectures on his, I think he translated Steinberg's book, and he gave a beautiful course on that. But we were both instructed to give a course. We were at the institute there, but we were instructed to give a course. And one of the things that I was thinking about at the time was these so-called Ramanujan graphs. And I had many discussions with Joseph about this. Another thing we would do is go on the bus to give joint colloquia at Beersheba, Haifa, and those bus rides were, as many of you know, who've taken trips with him, very mathematically enlightening. So at the time, the following had been come out was so another Israeli, Noga Alon, and Bopana had shown that you can create the biggest gap you could create in the spectrum if the graphs get large of 3 regular. They were working at general D regular, but this talk is just about 3 regular, is the interval 2√2, 3. So the fact that there's a 2√2, there's an indication that there's some calculation that I'll explain is involved there. So let me repeat what Alon Bopana theorem says. It says that if you take any bigger interval than 2√2, 3, then there are only finitely many graphs, 3 regular graphs that can have their spectrum gapped, so large gapped. And this particular topic of expanders, this defines an expander graph, has become really something that's should be second-hand or should be taught in undergraduate, the notion of an expander. And these are optimal expanders. And the feature that makes them optimal is that this gap can't be bigger, but what Alon Bopana asked and what was answered was that you can create a sequence of, infinite sequence of graphs which have 3 regular, which have no eigenvalues in this interval. And so this is a maximal gapped interval, and the definition of a Ramanujan graph is essentially one which is free of spectrum there. Sorry, I can't look at the question, so if there's any question that you want me to address by that way, please interrupt me. I'm very happy to be interrupted. So these Ramanujan graphs are constructed using automorphic forms. Using the solution of the Ramanujan conjectures, in this case for the graphs, all you need is the work of Eichler, who reduced the problem to the Riemann hypothesis for curves over finite fields. So the input is some very serious automorphic forms, that's why we call them Ramanujan graphs, as well as a Riemann hypothesis for curves of large genus, the theorem of Weil. This was found by Lubotsky, Phillips, and myself around that time, and Margulis independently while he was still in Russia. This is completely independent. I used to give lectures on this and say, well, this is very deep, and you would not be able to construct this without number theory, but as long as you make a statement like that, you will be proved wrong. And recently, it's not so recent, it's maybe 5 years ago, computer scientists who were not satisfied with the construction, even though they're extremely explicit and very useful, and we know a lot about them, they found another construction, and the construction is quite beautiful. It's due to Marcus Spielman and Srivastava. It was done while they proved the Catterson-Singer conjecture, which uses similar techniques. But in this case, there's an extra ingredient called the Li-Yang theorem from statistical physics, which asserts that certain polynomials have their zeros on a circle. Looks very much like the Riemann hypothesis for curves. It's a statistical physics theorem, which they input, and then a whole theory of interlacing. I should say that the basis of their construction is a conjecture of Bilou and Laniel, which I didn't believe at all, which says that you can construct double covers with good spectrum and hence make this infinite sequence. It's one of those things where Laniel assured me they did a lot of numerics, so it was well-founded, but it looked like a bit of wishful thinking. Of course, once it's proved, you can't argue. The proof of Marcus Spielman and Srivastava is quite beautiful, and it does not recover the full thing we know about number theory, from number theory. It does work in the situation where the degree of regularity is not of the form of prime plus 1, which is necessary for all these algebraic constructions using finite fields. So 3 is a prime plus 1, which is, in this case, fine. We knew these existed. And I will get back to the rest of the spectrum as we go along. Now, what I learned from Alicia and many others over the years is that the gap at the top, which is so important in this optimal expander, is not the only gap that people look for. And in fact, in physics, in sort of what's called tight binding Hamiltonians, and in some work that a paper of myself, Alicia, Fitzpatrick, and Haug, and there are other papers of this nature, the gap at -3 rather than at the top near 3 becomes important. And can you create that gap? And I will discuss that. And in chemistry, we have large carbon clusters, for example, fullerenes, which are planar graphs, 3 regular, where the faces have only hexagons and pentagons as in the sides. People look for reasons of Huckel orbital theory for a gap at 0. So the question that Alicia and I decided to start looking at is, what other gaps can you create? What other maximal gaps? And I'll explain to you right now that other people have thought around this. But before I do this, I want to discuss the gap at -3, because it's a very beautiful subject, which I didn't know much about until about 3-4 years ago when we started to look at this. And it's connected with root systems, and let me just explain it. So I'm still 3 regular, X is a space of 3 regular graphs, but for a moment, let me forget about 3 regular graphs. Let me talk about absolutely any graph. What time did I start? Gee, okay. Sorry, I just see the time. So suppose you take a
question. Can I interrupt you? Can I ask just a general question? So are you thinking about, I mean, are you asking a question for a particular graph? I mean, you said that you want to take the size of the graph to infinity. What is
I'm going to make a formal definition in a slide.
Okay, thank you.
And I will answer that exactly. It's going to be very formal. All right, but just let me talk about some work, what I'm going to call Hoffman graphs. So suppose you have any graph whatsoever, it's connected, you form its line graph. Its line graph means it's a dual graph. You take the edges, you make those the vertices, and you join 2 of those if they share vertex in common. So that's called the line graph. It's not quite a dual thing, because if you take that, it will go to something else, but it's called the line graph, and its spectrum is very closely connected to the graph of Z, the adjacency spectrum. So there's a factorization, there's something called the incidence matrix, and it's related to the fact that any Laplacian, which is a second order operator, factors, if anything's natural, into 2 first order operators, something times its adjoint. And that happens here. And so one can show that the spectrum of the line graph, this is just linear algebra. I learned from one of the speakers that the most important thing Joseph said that you need to know is linear algebra. This is what we're doing here. This is all just linear algebra. Consists of the eigenvalue -2 to a multiplicity, which is the number of edges minus the number of vertices, and then the spectrum of a new operator, which is related to the adjacency AZ. It's -2 times identity plus this diagonal matrix, which I'm not looking at a regular graph here. So this diagonal matrix this is an operator on the vertices. The operator has diagonal entries, the degree. So this DZ is just the degrees, the number of edges going out of each vertex. It's very easy to see this operator here is non-negative. So this spectrum is bigger than or equal to -2, that whole spectrum there. So it's a fact that the spectrum of any line graph of any graph is always contained in -2 to not infinity, there's the upper bound. But the bottom is -2, and -2 occurs with this multiplicity. So from this, you see that the minimum eigenvalue is greater than or equal to 2 for a line graph. And I'll call such a graph a Hoffman graph, because a combinatorist whose work is very relevant here, Hoffman, defined these and observed something very important here. So let me make that observation. You see, the minimum eigenvalue you can write as a Rayleigh quotient, a variational characterization. It's the minimum of X, A self-adjoint. So there's a realization this way. So if I take a subgraph, an induced subgraph of my graph, this is for any graph Z, this is the minimum eigenvalue. If I take an induced subgraph, which means a subset of the vertices and keep the edges which remain in the graph, that's just the same as taking some of the variables in this quadratic form to be 0, the vertices that you've omitted. And from that, you learn that your minimum is now taken over a smaller set. So the minimum of the smallest eigenvalue of Z is less than or equal to the smallest eigenvalue of B. But if the smallest eigenvalue of Z is supposed to be greater than or equal to -2, so suppose a Hoffman graph will be a graph for which the minimum is -2, then there are many small graphs. You can just start writing down very many small graphs whose eigenvalue is less than -2, and those graphs must be forbidden. So you immediately see there's a very good chance that you'll be able to actually classify graphs whose eigenvalue is greater than or equal to -2, and that's this classification. There's a beautiful paper that I urge you to look at, is that if Z is so this was this comment, if Z is a Hoffman graph, then it cannot contain a host of certain induced subgraphs. And in combinatorics, there's a beautiful theorem of Seymour and co that tells you about induced subgraphs. So structures of graphs, when you say certain induced subgraphs, and the more induced subgraphs you say can't be there, the more you're going to classify them. And this led to a classification by Cameron, Goethel, Seidel, and Schult in 1975 in a beautiful paper called Line Graphs, Root Systems, and Elliptic Geometry. They classify these line graphs as basically being, these Hoffman graphs as really have to be constructed as line graphs, or what are called generalized line graphs, except for a sporadic finite set of graphs. So when the spectrum is greater or equal to -2, they actually can set up a Cartan matrix, as you do with root systems, and show that the finite list of graphs which are not of this type actually lie in the E8 lattice as distances between vectors in the E8 lattice. But there's just finitely many such things, and everything I'm going to talk about, Sasha asked about the formal definition, which is coming, is when the graphs get arbitrarily large. So anything finite, that's of course of interest to many people, but any definition that I will give will be what's true in the limit for arbitrary large graphs. I'll make the formal definition in a second. All right, so to construct these line graphs, so that's a classification, and that led us in our analysis of the spectrum at -3 to define the following operation, which is a map from 3 regular graphs to 3 regular graphs, which is going to be one of our main tools to study what I'm about, all the theorems that I'll describe. And that is the following. It's to start off with a 3 regular graph, connected finite, subdivided by taking each edge. I don't care if it's plane or not. Put a vertex in the midpoint of each edge. So I now add these midpoints as new vertices. This will give me a biregular graph of degree 2 for these vertices and degree 3 for those. And then you think about it for a second. If you take the line graph of the new graph, which will have 3 times more than vertices than the original one, then it will be again a 3 regular graph. So this is a map from 3 regular graphs to 3 regular graphs. It makes the graph bigger. If I iterate this, the graph will get bigger and bigger. But it is a line graph, so its eigenvalues are going to always be greater than or equal to -2. So it's a way of constructing graphs which have a gap at the bottom. The gap at the top was this very difficult one connected with our Lon-Bopana. The gap at the bottom is really this, what I'm describing here. So as a consequence of that, and this is at the heart of everything we do, this is proved in our physics paper, that if you have a y and x, which is sufficiently large, it keeps away from those sporadic ones, then the spectrum is contained in -2, 3, if and only if y is in the image of this map T, or this subdivision and line, which is basically adding triangles at the vertices. So this is a very beautiful description of a spectral description of being in the image of this map T. So T is a map from 3 regular graphs to 3 regular graphs. I'm going to study its dynamics to prove any theorems. It seems people haven't studied this before, and the spectrum of any such graph in the image is -2, 3, it's contained in -3, -2. That's, sorry, no, it's contained, the spectrum is contained in -2, 3. So -3, -2, that interval, subset of -3, 3, that open interval in the induced topology, is a maximal gap interval. So we now have this maximal gap interval at 3 and a maximal gap interval at the bottom, which is -3 to -2. I'll make the formal definition now. So a closed subset of -3, 3 is a spectral set. So you're trying to engineer graphs whose spectrum has gaps. Gaps are desirable for many of these applications. So a closed subset is a spectral set if there's an infinite sequence of y's such that their spectrum is contained in K. And clearly what I want to do is find minimal spectral sets. The complement of a spectral set will be called a gap set. So that's, there's an infinite sequence of graphs which have no eigenvalues in -3, 3K. So spectral sets and gap sets are the same thing. And you ask, can you actually, is there a theory of what you can achieve here? So we seek these maximal gap sets or minimal spectral sets. So that's my formal definition. I repeat, infinitely many y's. So the y's must be allowed to get arbitrarily large. So that's the definition, and we're going to try to answer this. But I want to explain that this question has been asked in other contexts, and there are some beautiful theorems answering them, showing that things are a little boring in higher rank. So let me start with this. So I'm going to describe two similar situations and then show you how rich 3 regular graphs is. It's much richer than either of these, apparently. So the first is, suppose I take a higher rank Riemannian symmetric space, which I call S, or you could be looking at a Brouillard-Titz building of higher rank, and we're going to look at quotients of those. So these are not things that engineers normally order, higher rank symmetric spaces or Brouillard-Titz buildings, though they're becoming more popular because they're very rigid and beautiful structures for certain purposes. And there's a beautiful rigidity result of 7 authors. You can see them here: Aber, Bergeron, Beringer, Gerlander. I wonder if they all know all the co-authors. They call themselves anyway the 7 samurai. And they proved the following remarkable theorem, which will have some relevance at one point for us. So you have a higher rank quotient. So I take gamma, a lattice in the isometry group of this symmetric space, and I take a quotient. Finite volume or compact, doesn't matter. Think of compact quotient. And then the statement is, as the volume goes to infinity, no matter how you increase these quotients of the symmetric space, if it's higher rank, then, so that you could go through a congruence tower, but you could go through any way you want. You could change the definition. Of course, there's a famous theorem of Margulis, which says in higher rank, these groups are all arithmetic. But no matter how you go to infinity, and in these higher rank situations, there are only finitely many, just like in our cubic graph case, only finitely many of a given volume. So as the volumes go to infinity, these manifolds actually start to look like the universal cover. So in a way, it's boring. But this theorem is remarkable. That is to say that it's not true that locally, you might come back on yourself locally, but for most points, you will look, so if you take a random point in this big manifold, it will look like the universal cover. And this notion of convergence, where you look at what happens to most points in the manifold, is called Bignamini-Schramm convergence, which is quite general convergence for graphs, for example. And the theorem here, which is a remarkable rigidity theorem, is that you Bignamini-Schramm converge to the universal cover. A consequence of this, it's not difficult, is that then if you look at the spectrum, now in higher rank here, you can look at the spectrum of the full ring of differential operators if you wish. The spectrum will automatically converge as a measure. So if you have compact quotient and you put delta masses at the spectrum and you make a probability measure out of that, often called the density of states, if you take that, no matter how you go to infinity, no matter how you increase, the measure will converge to the Plancherel measure on S, computed by Harishchandra. And we know, so I'm looking just at spherical one, not the full Plancherel measure here, and I have a very important thing here, which is at least the tempered part. There's a non-tempered part that we understand, and let me not worry about that. So the tempered part, these measures will converge weakly to this Plancherel measure, and hence the support, which is what I was interested in, what gaps can you create in the spectrum? You can't create any gaps. The Plancherel measure is supported on the tempered spectrum in the spherical stuff with no gaps, and this will have no gaps. So in higher rank, you cannot create gaps. It's very rigid, it's very beautiful. The question is, what's the story with graphs where we have no rigid, where we're trying to find the lack of rigidity? There's another setting in which
about this result is somehow related to the fact that all gammas are arithmetic, or is it?
Yeah, it is absolutely. But it's stronger. So there's work of there's some very beautiful work of Freitschik and Finnis and Lapid, which discusses just the arithmetic cases, even when you in rank 1. And if you stick to arithmetic groups, then again, this features true, at least in SL2R, that's a beautiful theorem of Freitschik. If you go through congruent subgroups, that's due to Finnis and Lapid using the trace formula. So the answer is yes. But it's also connected with the fact that there aren't any sort of skewed covers. The covers are somehow want to be round and become like the universal cover. no matter how you make things arithmetically. I could go into that in connection with Ramanujan, generalized Ramanujan conjectures, but I just wanted to explain this rigidity. The answer is yes. The answer is yes. Let's look at something else, which has got to do with coding and Gopa codes, which was studied by Zafman, Fassmann, Vladut, Grunfeld, and most recently, Sir, just 2 years ago, wrote a very beautiful paper that's relevant to us. So suppose I look at the zeros of zeta functions of curves or eigenvalues of Frobenius of curves over abelian varieties over a fixed finite field. So if it's curves, I'll let the genus go to infinity. If it's finite fields, I would let, if it's abelian varieties, I'll let the dimension of the abelian variety define over fq go to infinity. But if q is fixed, the finite field q is fixed. So we're looking at situations. Now we know that the zeros satisfy the Riemann hypothesis. So the eigenvalues of Frobenius are size square root q. So we curves, there will be 2g of them, and they are located around the circle, and it's they're symmetric by the alternating. So I should have drawn that symmetric. I tried to. So you got these 2g eigenvalues for your given curve or your abelian variety. And the question is, can you, when you take bigger and bigger curves or bigger and bigger abelian varieties, keep a gap in the spectrum? It's exactly the same question. What gap sets can you have here? So this was asked and answered beautifully in the case of curves, the gap question at least, by Fassmann and Vladut to show that no gaps can be created. It's kind of like the rigid situation before. Key insight there with positivity of certain expressions involving traces of sums of the eigenvalues and counting points. This is very much used in order to produce curves with large genus over a fixed field, which have unusually large number of points, thus giving the best linear codes called Gopa codes coming from the algebraic geometry of divisors over these curves. This is why people want to construct them, and that's what the interest in this. So you have a very rigid situation if you have curves, but if you allow abelian varieties, then you have the Honda-Tate theorem, which allows you to say what kind of characteristic polynomials you have of an abelian variety of a finite field. And Serre made a fantastic insight here that essentially, and now comes a key word, transfinite diameter, out of nowhere. What is this? I'm going to explain in a minute. There is a condition that any set, so with abelian varieties, you can make gaps. And the sets, there's a limit to how small the set is in which it could be the analog of spectral in our graph case, in that the transfinite diameter must be at least q to the quarter. And then more or less it's if and only if by the Tate-Honda theorem, plus some remarkable generalization of works of Raphael Robinson that he gives. What is this transfinite diameter? It's going to enter into our work. There's a beautiful theorem of Fekete from 1930. Let me remind you what it says and its relevance to us. Suppose you have a subset of the complex plane, and suppose it's compact. The transfinite diameter or the capacity, it's defined at the bottom here, is a number. Let me go to the bottom here. So if I have the set K, it's a compact subset of the complex plane, I take all sets of endpoints in the set that I can find, distinct points. So the set will have to be infinite if the transfinite diameter is not to be 0. And I maximize this geometric mean of the products of the distances. And it's not difficult to see if I do this with n points and then n plus 1 points, the sequence's maximum decreases. So it's a decreasing sequence, and the limit, as you take more and more points, is called the transfinite diameter of the set. It's a measure of the size of the set. It turns out that using complex analysis, you can relate it to Green's functions at infinity, something called the Robin constant, and you can relate it to the capacity of the set, which is the capacity of the set is you try to make an equilibrium measure using harmonic functions on the set and on a large ball, which is going to infinity. But there is this measure of how big a set is, which is not the Hausdorff dimension, it's not the Lebesgue measure, it's much more suited to this problem. And here's a And I'll give you some computations of capacity. We'll need this in a minute, but here's Feketa's amazing theorem. Suppose you have a subset of the plane, which has a property that it contains, well, all right, you look at all algebraic integers, arbitrary degree, algebraic integers, which lie in the set, and all its Galois conjugates lie in the set. Then if the capacity is less than 1, that set's finite. There can only be finitely many such algebraic integers. And that's sharp. For example, if you take the unit circle, you have roots of unity, and that has capacity 1. But if the capacity were less, you wouldn't be able to produce infinitely many numbers inside there, all of whose conjugates also lie in the set. So the capacity, so in order to have a lot of algebraic integers and their conjugates in the set, you have to have capacity at least 1. It's a beautiful theorem, and it's been generalized by Tsego. There's a theorem of Feketa and Tsego, and there's a theorem of Robinson, which is a converse that generalizes. Now, what's the relevance to us is there's one thing about the eigenvalues of a graph, of a finite graph, is that they are algebraic integers, because a characteristic polynomial has a leading coefficient x to the n, and it's got the polynomial's got integer coefficients. So the roots and all the zeros are totally real algebraic integers. So they're real numbers, and they are algebraic integers. So that's something nobody's really been able to use as far as I know. And we will be using it. Now, the way Serre uses it in the setting of the abelian varieties is to use it that by the Riemann hypothesis for varieties of a finite field, or more generally, the eigenvalues of Frobenius are in any complex any embedding into the complex numbers of a fixed modulus. So they lie on a circle, and all their conjugates lie on the circle. So that's where the capacity, or this transfinite diameter, comes into his theorem, and it's certainly going to come into our theorem. By the way, I'd forgotten about Serre's paper. We'd kind of been writing this, and then I was looking at the literature and found that, of course, he'd seen this in that other context. All right, so now I want to state our theorems and say words about the proof, and I think I'll be done. I think I have 15 minutes, is that correct? 14 minutes. Is that correct, right?
Yeah, take your time.
Okay, so our first theorem was, can you make every point in -3, gapped? In other words, is it true that you can find a neighborhood of every point? So 3 is always an eigenvalue, but for any other point, can you find a little neighborhood? And then a sequence of graphs, 3 regular graphs, arbitrarily large, infinitely many, that is, so with no eigenvalues in that set. And the question for just making it gapped is not so difficult, but the question to make it planar gapped, planar graphs with this property, is one of our main theorems, where we use everything that I'll show you to prove that. So that's true. You can create gaps at any point. The second is this immediate consequence plus a little argument of Feketa's theorem, that a spectral set, so you might think you could make the spectral set, you might think you could make 3 regular graphs which have which are spectral, meaning that you can find some very small subset of -3 and an infinite sequence of graphs with their eigenvalues in that small set. Well, the answer is no, you can't. By Feketa, the capacity of any spectral set must be at least 1. That's the immediate consequence from the fact we're now using this Diophantine property of Feketa. So spectral sets can't be too small in sense of capacity, and every point can be gapped. And now we want to do what Alon Bopana do, and what I was explaining in the Hoffman situation, is can we find maximal gap sets? And the answer is we do. There's some miracles, and I'll explain to you where they come from. So I mentioned that the gap at 0 was something that's of great interest in chemistry, and we found these. These are not going to be so useful for chemistry yet, as you will see. So we show that we discover 2 new maximal gap intervals. So -1, 1 is a maximal gap interval. I repeat, that means that there's an infinite sequence of graphs, 3 regular graphs, which have no eigenvalues in -1, 1. So this is like pushing the eigenvalues out of the middle. These are all bipartite, and any bigger interval does not have that property. So if I went from -1 minus delta to 1 plus delta and asked that there is there an infinite sequence of graphs with eigenvalues gap in that slightly bigger interval? The answer is no, there are only finitely many such graphs. So there are two parts to any such statement. Just like with the Alon-Bopana theorem and the Ramanujan graph, you A, need to construct the graphs with such a big gap, and B, then combinatorially prove that you can't do better. And so these are two maximal gap sets that we have found by, Alicia has a way of finding these, as I'll explain in a minute. And there are miracles connected with this, which I think are very much connected to features similar to supercuspidal representations. I'll explain in a minute. So there are miracles which allow us to construct these, and then there are combinatorial proofs that we give to show that they are optimal. And now I want to give you kind of one of our main tools to prove any of these theorems, especially the fact that everything is gapped, is this map that I described to you from 3 regular graphs to 3 regular graphs. There may be other interesting maps whose dynamics need to be analyzed this way, but this is what we do. And remember that map T, which first divided and then line graph, is very explicit in its construction. So one can compute quite easily what the spectrum of the new guy is in terms of the old guy. And it turns out the spectrum of T of Y, which is got 3 times more vertices than the starting graph, is the inverse image under this rational map of the old spectrum. And it always adds 0 to n is always even. It adds 0 and -2 with high multiplicity. So when I go from Y to T of Y, I will introduce these eigenvalues 0 and -2 with certain multiplicity. And then the rest of the spectrum is the inverse image under this rational map, and we immediately going to have to worry about rational dynamics here, which will play a big role. So our proof makes use of this dynamics of T on the 3 regular graphs and the dynamics of this nonlinear rational map, which is not a difficult one to study in terms of people who study rational dynamics. It's nothing like a Mandelbrot set here, as you'll see in a second. Here's the actual rational map. It's got 2 fixed points, -1 and 3. They are unstable. So if you start off with a random point here and you start iterating f, you will go off to infinity. You'll eventually get outside of this and you'll bounce off to infinity. Here you'll go around here and then bounce off to infinity. But there is a Cantor set in which you'll get stuck, an invariant set on which the dynamics of f is completely chaotic, and it's very easy to identify, and it plays a big role in our proof. So that's the dynamics. And so let me define this Cantor set. So if I take the inverse image of -3, 3, you compute that. It's just these two disjoint union of these two intervals contained in -3, 3. And each time I take an inverse image of under this, the set decreases, they closed, and they become more, becomes a Cantor set. And if I take the intersection, I have this non-trivial Cantor set whose Hausdorff dimension actually I haven't computed. I was going to compute it thinking it's relevant, but the capacity is what's much more important in view of Feket's theorem. And so there's a Cantor subset of, which is the set lambda, such that the dynamics of f, if you take any point x, which is not in the Cantor set, and I start applying f, the point will go off to infinity. On the other hand, the restriction of f to this Cantor set is topologically a shift on a sequence space. So it's a Bernoulli shift. It's very complicated, but very explicit topologically, and we use it. And now comes the most amazing set that we've discovered. I'll call it A, which is this Cantor set, union this infinite sequence of points which accumulates onto the Cantor set. As you saw from the formula, I will be looking at inverse images of 0. So this is a countable set of points. They are isolated in the set A. A is closed, and these points accumulate onto lambda. So A is a closed set. It's got these points as isolated points, and that is a Cantor set. And this set A has some incredible properties. A is a minimal spectral set. It is a spectral set, meaning there is an infinite sequence of graphs, 3 regular graphs, whose eigenvalues lie in this Swiss cheese, in this very thin set. So as a gap set, it's massive. You can create these gaps. Its capacity, incredibly, is 1. This was one of the joys when you do these sort of things. Remember that that's as small as it could ever be, so it's completely optimal. It's a minimal spectral set in the set of capacity. And in fact, if you look at all the Y's whose spectrum lies in A, they lie in finitely many T orbits. So this map T, they're infinitely many orbits there, but they're all T's explaining everything. And because this T has got this property that if you have a spectral set, then you take the inverse image. This is explaining again the fact that the dynamics of F is so important in understanding the dynamics of T on the space of graphs. I see I'm running out of time. There's a proposition here which is going to be used in the proofs. I'm going to just give you a picture of the proofs, but I want to just spend some time on what we understand and and some theorem which is connected with Binyamini-Schramm convergence. So in some sense, we're trying to understand what are all the Binyamini-Schramm, trying to understand more than that, but the first step you would want to understand is what all the Binyamini-Schramm limits of 3 regular graphs or 3 regular planar graphs. These are fundamental questions. They're not understood, and this is what we're getting out, opening the door but towards. So far, we've found maximal gap sets in the spectrum of 3 regular graphs. There's the Alon-Bopana, there are these 2 new ones we found here. There's the Hoffman one over there coming from line graphs. And it becomes a fundamental question whether you can realize this with planar graphs. So the Hoffman you can realize with planar graphs. I explained that with the map T. The way we show that -2, 0 and -1, 1 are gapped, the construction, which I'll give you in a second, is we don't know how to achieve it in planar, and we don't know if you can. You cannot achieve the Alon-Bopana gap with planar graphs. This is a famous separator theorem in combinatorics that planar graphs cannot be expanded. So not only can you not achieve that gap, you can't achieve any gap near 3 with planar graphs. That's a important combinatorial fact. So these are maximal gap intervals that I know, and then you can apply F inverse to create new ones from old ones. Yep. And the minimal spectral sets here. Now I want to just say a word. So A I just described. And this new minimal spectral set, this old minimal spectral set that you can find an infinite sequence of 3 regular graphs, all of whose eigenvalues lie between -2√2, +2√2, and 3, not bipartite. That, of course, constructed uses number theory. And here's where I can still say that nobody's constructed this except using the Riemann hypothesis for curves, because the Marcus Srivastava Spielman proof does not provide these examples. And let me add one more thing here, is that there's a remarkable theorem, which I think I'm a big fan of, has not quite been noticed enough by Eber, Glasner, and Virag, which is similar to that higher rank thing. And that is if you have a sequence of Ramanujan graphs, their spectrum lies in here. So we know there are infinitely many Ramanujan graphs. We only know how to construct these using number theory. But suppose you have such a sequence. They prove that you can't create new gaps. In other words, if you have a sequence of Ramanujan graphs, the eigenvalues must become dense here in that. And the way they prove that is they show that a sequence of Ramanujan graphs, Binyamini-Schramm converges by itself to the 3 regular tree. It's a beautiful theorem showing a rigidity. Once you restrict the spectrum, then you have to Binyamini-Schramm converge to the tree. It's kind of a converse to things that are new. It's quite beautiful. And it shows, and using that, one learns that this spectral set is a minimal spectral set. You make any smaller closed set, it cannot carry an infinite sequence of 3 regular graphs with the eigenvalues there. So this is a minimal spectral set, which we think has got the maximal capacity. And A, I've already told you, is got the minimum capacity. And the map F interpolates between them. So we don't have too many other spectral sets, but we can create new ones from old ones. So I see I have maybe 2 minutes. Let me say a word about how we prove these things. I should have given more time for this. So the map T is very critical in creating a lot, mixing things up and its dynamics. But we need some points to start working to make gaps and create new gaps and create gaps. So the gaps at the Alon-Bopana gap is a deep one to construct, and we only know how to do it in general using number theory. These gaps are very much engineered in a different way. And there's a natural way, and physicists know this very well, and we all know this very well, is we look for abelian covers. In fact, cyclic infinite covers for which we can maybe understand the spectrum and then conclude from that what the spectrum of finite quotients are like. In physics, these are called Bloch waves. You might call it Foucault theory. In mathematics, these are abelian covers parameterized by zero sets in tori, which is the dual group of the covering. The real thing here is not these where you go look. The thing is, what do you find? And this is where Alicia finds gold. So the construction, for example, of these gap sets come from these over here. So let me just explain this picture. So look at the bottom here. This is an infinite cyclic, infinite three regular graph. It's clearly got a periodicity by shifting by Z. It's a cyclic cover. And the question is, for this infinite cover, can you compute the spectrum? And the answer is yes. This is what this Foucault or monodromy or Bloch wave theory gives you, is that there is a torus, and in the torus, which is one-dimensional here, so you have eigenvalues which are functions of the twisting parameter. It's a flat bundle, if you wish. And I want to tell you what the miracles are. You start at 0, so the eigenvalues are at -3, -1, 1, and 3. Now you switch on this twist to make an infinite sequence of cyclic covers. To make finite things, you just take quotients of this. And you're hoping that when you switch on this rotation, that the eigenvalues, the bands, these eigenvalues keep the gap. And that's very hard to arrange. Mostly it doesn't happen, but a miracle happens here. So you start here at 0, which is your starting graph, which is that one basically. And it's got an eigenvalue -3, -1, 1, and 3. It's bipartite. And here's the miracle. The eigenvalue at -1 and +1 don't change when you vary theta. This is very much a supercuspidal feature. I don't understand other than when you see it, you're very happy. You can prove it rigorously. This is not an issue. But this is a miracle. These they're called flat bands. They don't change. And this gap stayed throughout this infinite cover. So this means that when you take your finite quotients, you get no eigenvalues between -1 and 1. Fills out this. So the miracle was the other eigenvalue over here. When it came up here, it didn't cross. It stayed underneath. And the flat band seems to want to force that. And the existence of flat bands should have a much better explanation. Once you find it, as I say, it's not difficult to find, to prove. I'll tell you that I won't tell you the secret of how we find these. And then there's a similar gap over here. It's a bit different. Remains a gap over there. So basically, you need an arsenal of to prove that every point is gapped. We need a starting arsenal of graphs, maybe planar graphs with nice gaps in their spectra. You can't use abelian covers directly to ever make gaps near 3. That's because abelian covers will not allow you to gap at 3, and it becomes extremely difficult to do anything near 3. So, for example, here, these cover all the range from -3 all the way up to 2√2, in fact, by explicit examples that were found and these Bloch waves computed. But then to get from there to there with planar construction, we have to use the nonlinear dynamics of F to build up new graphs, which will create gaps at the top there. So the abelian, as is always the case in any kind of harmonic analysis or class field theory, the abelian stuff you can actually control. Just how rich they are, we don't understand. One of the main mysteries to us is when these flat bands, which are sort of where the eigenvalues don't change, they correspond. Why do I say they correspond to, in some sense, supercuspidal? The eigenfunctions, so let me repeat here, the eigenfunctions of the adjacency matrix on this infinite cover over here actually are compact support. They are compact support eigenfunctions. They're drawn in this picture here. And these flat bands are essentially equivalent to their being compactly supported eigenfunctions on the quotient. And we all know that compactly supported eigenfunctions have a very special role, and they are playing the role to somehow keep these things apart and push the other guy away, keeping the gap, creating some kind of miracle. Of course, then you have to go and show separately, combinatorially, that that's the biggest gap that you can have. All right, I think I've exhausted my time. I go back to Joseph. I'm sure he will explain what I'm doing. But conceptually, the problem is very clear. We want to make what gaps can you create? And I have a feeling that there's a much deeper explanation of these flat bands and how these, so far these have been found just by looking at small graphs and their abelian covers to make these constructions. And this table should be filled out, I hope. Where's that table? With more sets. And of course, if you put the more conditions you put on the planar graph, the harder it is to make a gap. And there's clearly a very rich theory here. So the moral of the story is 3 regular graphs are not rigid like higher rank. They're not rigid like curves, Frobenius of curves. They're not as flabby as abelian varieties. They're somewhere in between rich and apparently useful. And with that, let me end and thank the organizers again and wish Joseph many happy returns of the day and many, many more insights for us. Thank you.
Thank you. Questions?
I have a very naive probably question. Can you somehow give us some intuition about the map T? Because somehow for a person who doesn't have a lot of experience in combinatorics, this looks like a very crazy map. For example, does it have an analog, for example, for symmetric spaces or something like that?
Right, so you can make the map for any D regular graph. I don't understand, it's basically, the way to think of it is you take each, so if it's a 3 regular graph, you take each vertex and you replace it by a triangle. Sorry, I don't have a means of writing. I had thought of putting my whiteboard behind, but so you'll just have to let me use my hands. You take you've got a 3 regular graph, and you can do something similar with the R regular graph, D regular graph. You take each vertex, you put a triangle instead of that vertex, and originally there were 3 edges coming out there, and you use those edges to dictate how you connect to triangles. You put triangles in each vertex. And so when you iterate this map, you get to, locally, you start to look like something called the Hanoi graph, for which is quite a history in terms of Hanoi puzzles. So the local structure and the Binyamini-Schramm convergence of iterative T is kind of obvious. What is not obvious is how the full spectrum is behaving there. So this map T is something I don't understand how to generalize. And I'm sure that when you understand this problem properly, it will be connected to constructions of algebraic integers lying in sets. So I should say there's a beautiful theorem of Estes that every totally real algebraic integer is the eigenvalue of some finite graph. So you could,
Sorry, can you say it again?
So this is a conjecture of Hoffman proved by Estes maybe, I don't know, 20 years ago. And there's a beautiful treatment by Hyman Bass of this thing. And that is that he conjectured, well, the first observation that we were using here was that the eigenvalue of any, is this like a Veil number, but there's no algebraic geometry. The eigenvalue of any finite connected graph is an algebraic, a totally real algebraic integer. All embeddings are real because the roots of a polynomial, the eigenvalues are all real, symmetric matrix. And the converse is true. You can always, given any totally real algebraic integer, you can find a graph with that eigenvalue, the number you give. But 3 regular graphs are very restricted, and this map T has got to do with 3 regular graphs. So my feeling is that maybe you're first supposed to solve this for all graphs, and that would be very much along the lines of what Sarah and Robinson are doing, which is to understand which sets contain algebraic integers and all their conjugates. Which is one question, and you've got the freedom of making any algebraic integer. So there's the one constraint on the transfinite diameter and the capacity, but otherwise it's not rigid. But for 3 regular, I only have the map T. So the answer to your question is I would love to find more maps to do dynamics, and that would allow for a much, I think the theory is quite rich. I think that the set of limits of 3 regular graphs, how they look when you take large, is extremely complicated. And that's what we're looking at. So what is much easier is if you take a random 3 regular graph or a random map, planar map, which probabilists like to do, and then they all Binyamini-Schramm converge to much more controlled things. But we're looking at what you can engineer by some subtle, skewed looking thing. And the thing we're making most our living from are these long sausages of cyclic covers, and then mixing them up with T. So the answer is I don't have a full, I gave you a description of T, but I would love to find more T's, yeah. I would love to find more operations on the space of graphs whose dynamics is decisive, yes.
Thank you.
You said that in theorem 3, you have finitely many T orbits.
Yeah.
So you might be able to draw the simplest representative of a T orbit.
Yes, yes, absolutely. I'll tell you what it is. I do know what it is. It's the actual complete graph on 4 vertices, each joint. That's a starting guy. And we found actually we have 3 orbits so far. There are only finitely many orbits. The list could be very large, but we found 3 distinct orbits so far. And the simplest one is to start with a complete graph on 4 vertices, 3 regular graph, and then apply T to it repeatedly. Yes, the answer is that's the simplest. It's the mother of this, yeah.
Thank you.
What about the operator that takes a graph and replace it with a tubular neighborhood, a surface, which obtained as a tubular neighborhood after some, locally embedding it in R3, and relay the spectrum of the graph and the spectrum of the surface? Is there any?
It's a good question, but let me, I deflect. Let me just say this, that you can ask the same question, and I'm sure it's very rich and beautiful. Suppose I take a sequence of hyperbolic surfaces and ask, what can you say about the spectrum of what gaps can you create in the spectrum of the Laplacian? So Selberg's conjecture says if you are a congruent subgroup of SL2Z or any arithmetic thing which is in Bajaquet, Gelbart, Lift, any sort of quaternion algebra there, that the spectrum, the smallest eigenvalue, lambda1, is greater than or equal to a quarter. We don't know that, but we understand that that should be true. It certainly follows from functoriality. But then the question that the analog question, which I'm sure is very interesting, is what gaps can you create inside the spectrum with hyperbolic surfaces? And what gaps can you create between 0 and a quarter if you're not arithmetic? Those would be the exact analog of these questions. And I'm sure it's a rich theory. And it's again a theory of not Binyamini-Schramm converging to the universal cover, because then you can't create gaps in the tempered spectrum. But what you can create in the tempered spectrum is probably by taking some weird surfaces which are converging. But the passage between the discrete and the continuous, which you're asking, there are some works of Brooks and people like that, and Mirzakhani. I don't know that they are sufficiently strong to study this kind of question. They're more about somewhat cruder bounds, like a spectral gap at the bottom, like an expander property. There's Bob Brooks was the first to discover the relation between amenability and non-amenability in terms of the universal cover and the spectral gap at the bottom. but it's a good question.
Just to add to this question, it seems to me natural to look for operators T in that other space of surfaces, not of graphs.
Please find them, and if you do, I'm all ears. Okay, I'm sure there exist many other operations which would make what is a very rich theory. I think we just at the surface of what's a rich theory. Yeah. But anyway, the engineers want to create gaps. That's really fundamental for stability of a carbon cluster. And so they want to know what kind of gaps you can create and what kind of gaps you can't, and what kind of gaps you can create with extra conditions. And this is an engineering problem, right? And any operation on the space that you're working with, as we all know, changes the way you think about things. So T is just hopefully one of many, but it's all we have at this point. Also, you need to be able to understand how the spectrum changes when you apply this operation. And that's this rational dynamics. This is all somewhat elementary, but I think it fits together. And the capacity, at first we were trying to prove Hausdorff dimension, extreme. All of a sudden capacity was, why haven't we used capacity? And once that was used, it's married to this problem. It's absolutely married.
I have a question. If you take any trivalent graph, which has like 3 outgoing edges, and you have symmetries exchanging the edges, then you can define an operation where you replace every vertex with a copy of your graph. Like you just choose any graph, and you just cut away every vertex on your graph, and you replace each vertex with a copy of that other graph.
Okay.
And so the operation you have is an example of those. And so it's like, did you check the other operations, and do you know that they don't get you interesting spectra, or they do get you?
No. I would say almost certainly it's interesting. I didn't even think of that. I've been living off T for the last few weeks. T is good, and more of T will be better. I know that you guys look at these. There's something worth pointing out here. So Will Seven, who's the guy speaking there, has this generalization of you and Puda, right? Have a generalization.
Chris Hall, yeah.
And Hall, yeah. Have a generalization of Spielmann et al., where they look at random covers and make these, not random, make these covers with this property of gaps. So what you do there, at first I was a bit confused. You make sequence of abelian covers. You make double covers. So you start with a double cover, that's abelian. But then you take the new guy and you take a double cover of that. When you do that repeatedly, this is what Bilou and Laniel conjectured, that you can always find double covers with spectrum outside 2 root 2, 3. Yeah. That's not described at the base by one infinite sequence, not abelian over the base, but it's abelian at each step. And that's already sufficiently rich to give a new construction of Ramanujan graphs. So we need these operations which make new graphs from old graphs and be able to follow the spectrum through that. So the fact that you can follow the spectrum through such a construction was the big insight of Spielmann et al., and these guys generalize that. The fact that you can do it through abelian covers is not surprising, but it's very much related to other gaps. So I agree with you. I haven't thought about that. I suspect not that the answer is no. It's not that, oh, that doesn't work, it's not interesting. That probably is interesting. Okay.
Peter, can I ask a question?
Yeah, with pleasure.
Yeah, so have you been looking at a kind of weaker condition of gaps, which means intervals which contain very few eigenvalues rather than eigenvalues at all?
Yeah. So that's very much, so one way to show that the gaps become, so when I was talking about this theorem of Vladut, yeah, this. There's theorem here, Vladut and Fassmann and Grunfeld, I think, was also involved in some part of this. So the question is what gaps you can create there with curves. You can't create gaps, but then they ask exactly what the first question of what you're asking is, all right, let's make the measure. Let's put a delta mass at each eigenvalue here, or each Frobenius eigenvalue. And let's divide by the number. That's a measure, probability measure on the circle. And you could ask, what are the weak limits of these measures? And that would be exactly what you're saying, throw away everything which is zero density. And in fact, that's what they study. They show that the weak limits of these measures actually have support the full circle. While for abelian varieties, that's not true. But for this, they're sufficiently rigid that for curves, they have to be support the full circle. What they don't know, and what is, I think, related to your question, is what are the possible measures that you can get here? That's a major unsolved problem that they all seem very interested in. What measures can you get as densities, what I would call these probability densities? Now, if the probability density, if every single limit, there are different limits here, if every single limit is got support the full circle, which is what they prove, then you don't need to know what the measure is, but it's used along the way to get the density. So the answer to your question is, I'm interested in a more subtle question of no exceptions, but this is the first step towards your question. And I don't know what the weak limits of 3 regular graphs are. That's more or less equivalent to say, what are the Beniamini-Schramm limits of 3 regular graphs? I think that's a very hard question to classify that. That's the space in which, by the way, T extends to the boundary. So once you have your operations T, there's some juicy stuff. You'll find fixed points on the boundary on these Beniamini-Schramm probability measures. So any operation like T must be studied on the boundary. And in fact, we're doing that right now.
So do there exist sets which are not gap sets, but which still you can construct a sequence such that the limiting measure has support away from those sets?
I will have to think and email you. That's Pavel. Who's talking?
Yes.
I will. That's a good question. I don't know if it's a good, very good question.
Okay, thanks.
So, I have a question. Is there applications of the existence of these gap sets to quantum gates and quantum computation? So, for example, your paper.
Yeah. So all the applications that I know to quantum computation or to codes or to
building efficient universal gate sets or golden gates, as you call them.
Those all have to do with the gap at the top, which is always responsible for some random walk being very quickly mixing.
Exactly.
So I think I don't want to. I've wondered about this for years, but I don't want to diminish the importance of the Alon-Bopana gap or the spectral gap at the top. It's by far the most powerful and hardest to find. I was just taken by the fact that a lot of engineering problems require gaps elsewhere. So I think these other gaps, and they are very different. The random guy tries to mimic the gap at the top. The random guy certainly doesn't create gaps anywhere else. So I think all these other things are very much have to be engineered. So the answer is the only way I know that it's relevant to coding and quantum gates is the gap at the top, not at anywhere else.
No, right. Okay. And there's a question. So, well, in statistical mechanics, Bloch's theorem basically says that where there's a band structure in the eigenvalues of the Hamiltonian in a crystal.
Yes. Absolutely. This band, So this is baby Bloch wave theory. The bands are just the images of these. So in this case, there are 4 bands, 4 eigenvalues, and the bands are what they sweep out. So the band here would be -1, -3 to -1 would be one band, and 1 to 3 would be another band for this infinite thing. And remarkably, there are localized states which have to do with this flat band, which I really think needs a much deeper understanding. I want to know when
that was the question. Do these flat bands show up in actual physical crystals?
Absolutely. Yeah, that, I learned that from them. They call them flat bands. I would have never thought of such a clever terminology. Look up the miracles of flat bands in, especially around honeycomb, Kagami lattice, solid state physics. Yeah.
Okay, miracle of flat band.
It's very important, flat bands, and they're playing this role here. And I'm telling you that my gut feeling is there's a much deeper understanding and connection with somehow why they want to be flat. So if this were a cohomological problem, I mean, this would be like the discrete series. You take the infinite thing and there's a compactly supported eigenfunction. Harishchandra was so taken by this that that this non-compact semi-simple group can have discrete series is absolutely stunning. So these need explanation. When they're there, they are miraculous. And by the way, these are compactly supported eigenfunctions corresponding to the flat band. They are driving our
Peter, can I also ask, you said that random graphs do not create gaps away from this gap at the top. So, but is it known what the limiting measure is?
The theorem of Mackay. Mackay's theorem is that the probability measure I just described to you, which is on the eigenvalues, will accumulate on -2. It will be the random graph. Binyamini Shram converges to the 3 regular tree. The random 3 regular graph. So the random graph spectrally and without forcing the exact gap. So if you allow exceptions, just in density, that's an old theorem of Mackay. And in a sense, Keston computed this measure and Mackay computed this measure, which is the density of states for the 3 regular tree, which is the Plancherel measure for the 3 regular tree. It's also computed by representation people like, well, I'm sure you guys know. So those were computed separately in different communities. Mackay computed combinatorially, Keston computed in connection with random walks, and maybe Sally computed it first for p-adic SL2 of PGL2QP.
And
so yes, the random measure will converge to the measure, the Plancherel measure.
And it is continuous on this interval?
Yes, it's continuous between -2√2 +2√2, and it, absolutely continuous there. And of course, it doesn't pick up 3, because that's on the universal cover. Yeah, it's a beautiful measure. It's the Plancherel measure. It's the driving seat guy. Yeah.
Okay, if there is no immediate question now, let's thank Peter again.
Thank you. Thank you very much. And happy birthday, Joseph.
Joseph's here.
Thank you.
Okay, so since we are off the schedule, I suggest we first of all finish the conference, then we'll immediately take a photo, then we will have a 10-minute break and reconvene with wine.
I have a suggestion. Let's continue this conference forever.
Yeah, on technical levels, there's no problem with this.
I agree. Yeah, I mean, like I really have it's the first conference where I feel that I really want this thing to go on.
Where you feel at home, right?
No, it's just very inspiring and interesting. I mean, it's like
I'm curious. How do you take a picture? What's that going to mean? Well, I guess
I'll send you the result. So let's take a picture. For this, you need to turn on your video, locate yourself inside of your screen. Okay. Then give me a second.
Can you remove me from sharing screen? Get rid of me.
Yeah, I removed you already.
Okay.
So, but please turn video on. Okay, because people who will not turn video on will not show up. Okay. Now you smile. And continue smiling because there is a lot of people. Continue smiling. Don't leave the screen.
Say something funny. Say something funny.
Think about the wine.
Uri, here's something funny for you. Let epsilon be negative.
Okay, just give me a second to check.
Maybe we should ask Peter a question whether internet is an expander and what is the gap at the top.
Amara, where are you?
Gap is the gap in the proof.
Okay, I think we are done. Okay, thank you. Now we can continue.
So what's now?
Okay, so first of all, since the official part is off, so I want to thank all the speakers who came and gave beautiful lectures. And among the lectures, I would like to thank especially Misha Finkelberg, who triggered us to organize this this conference. So thank you very much. I'm not sure he is still here.
I can try to call him and urge him to.
He is here.
Yeah,
I just saw him.
Yeah.
He's here.
Okay,
He's here.
So yeah, thank you very much for participants and a lot of participants coming. We thank you very much our secretary Efrat, who helped us a lot with managing all this thing. And the last is, and maybe the most, we thank Joseph for his mathematics and for his beautiful mathematics, his generosity, his optimism, and for teaching us a lot about what we are doing, really. So thank you, Joseph, and happy birthday and happy productive years to come, so that we will continue doing this forever. Thank you. Okay, we will meet in 10 minutes. You grab your wine, coffee, food, whatever, and we will have those who want will have a discussion. And meanwhile, I run Joseph's photos, which we collected.
And thanks again to the organizers. It was very well run and very successful.
Yeah, no, that's what I said. I think it should definitely be continued forever. There's just no question about it.
Okay, guys, see you in 10 minutes. Yep.
Okay. Oh, хорошо. Дети.
Сделай, пожалуйста.
Ой,
Ага. Это с кем это? Ты?
это Гетикин.
Ау. Андрей немножко причесал этот альбомчик по-другому.
Андрей.
Это я. Фотография тоже. Так, Оська, вот твоя тарелка. Рюмка. Нет, так не получится. Я не зря... Тоже красиво. Отодвинь это все. Все. Отодвинь. Разбираться будем потом.
Дима.
А это на этом пресс-Исраэле или что такое?
На раме. Это тоже беспросветно.
Тарелки, крекеры, клубника, помидоры и выпивка. Да, это или это просамет?
Просамет.
Это
Да.
С Кирилловского этого. А это с Митькой?
Митька.
Я не знаю.
Это Тингов.
Угу.
Это я. Это другой Митька.
С Митькой. Фукс такой большой. Кстати, Ирка мне ничего не пишет, надо узнать, что у них там.
Это я не знаю.
Кто-то там эти наверняка сфотографировал где-то. Чего?
Почему ты там без скипы?
Это кто?
Здесь
это ты точно.
Тамар, или по-английски, или звук убери. Все то же самое.
Ага, окей.
Handsome guy.
Sixty-two.
This is 1987.
1987
in Zeus.
And cycle. You're right.
Date.
И root. Sarnak
Компьютер. Это самое.
Низирус.
Низирус.
Этот Люботский.
Ну, это Касуман.
А, это был. Я согласен. 72. Ага, ага.
Может, пора кончить.
Ну, сейчас народ соберется.
Это все прикольно.
Угу. На фузе. На фузе.
Фуджи.
Как будто.
Там написано, что это кабуки.
Кто знает, поймет. Это шишим. Это с губой такой. Только что подрезанный.
Okay, so we'll start our formal dinner. I'll finish these beautiful pictures. Okay. And Dima will say a few words.
Okay, so Joseph, I wanted to thank you again for everything. And I also wanted to say that Joseph is like a mathematical rabbi for us. And every rabbi has to have many things, but one of them is a rabbinit, which is his wife, the first lady of the community. And I wanted to say that Tamar definitely takes this job very seriously. She is our great rabbinit. So I want to raise this glass of wine to this magical disappearing glass of wine to Rabbinit Tamara.
Thank you very much, and thank you very much for the last difficult period when even each one from Joseph's students called us and asked us if we need something. It was so touching. Everyone prepared to bring food, to bring things, and it was very, very touching. And I can say that this work of growing students, growing like children, it's worth. Thank you.
L'chaim. L'chaim. Also, two people told me that they are not sure they will be able to stay, but so first of all, Steve Miller, are you here by chance? So if not, then I will try to find his email and say what he wanted to say. Yeah, I think I found it. So I also want to share a photo. All right, so I'll do my best to share it. Yeah, so. Am I sharing screen?
Yeah.
Okay, very good. So let me now read what Steve wanted to say. Okay, so I guess so here's what he wanted to say. Shalom, Joseph. I have much longer remarks. I will leave for your 80th birthday, but I want to congratulate you on this milestone. You have changed my life by introducing me to some amazing mathematics. But what's made a bigger impression on me is how nice and unintimidating you are to younger mathematicians. Thank you for always treating us with such respect. Okay. Now, another email of Dipendra Prasad. Dipendra, are you here? Okay. So if not, let me read his short address. So here's what Dipendra Prasad has to say. I knew Joseph during my days at Harvard in the late 80s, and although I did not have so much interaction with him, his kindness and generosity was all too evident. He did emphasize the importance of multiplicity one theorem in my thesis, and also gave a quick outline of how they are proved, including a key example, the union of x and y axis with the action of the multiplicative group. When mathematics has been becoming increasingly incomprehensible, it is such a blessing to have Joseph around who can get the key ideas through the simplest examples. Thank you, Joseph, for being such an inspiration, and happy 75th.
Thank you.
Okay. Now, whomever else wants to speak, please do.
Dima, can I say a few words?
Of course.
Well, let me say two things. One will be sort of serious and the other will be less serious. The serious thing is that I think that I was never a good student of Joseph, and I kind of, with the years, I understand this fact better and better, because well, Joseph has a lot of different strengths, but one of them, which is I think extremely rare, is the very, very clear ability to distinguish the things that you understand from the things you don't understand, and to separate them. I think very few people somehow have this ability, and not just in mathematics, I mean, in all aspects of life, but
yes,
especially in mathematics, this is, and you know, we recently discussed it with Misha Finkelberg that somehow one of the things which sort of is difficult for us, I mean, very often when we try to do something together, is that there are a lot of things which we feel that we sort of know, but somehow when we try to work with them, it turns out we don't know them. And the real problem is that somehow you never know in advance what you actually know, what you actually don't know. And I think that Joseph actually himself, when he talked to us about some things like this, he attributed this to Gelfand. And so, but I think that mathematically, one of the extremely rare sort of technical tools that Joseph was always able to perform, I would say, is the ability to take one example, and one very simple example, and to understand it really well, and from that build up somehow huge, complicated theory, but based on just very good understanding of one example. And I have almost never seen people who would be able to do the same. So that's kind of the more serious part, and the less serious part is that maybe Dennis will continue what I'm going to say now. Is that I remember that back maybe 20, 25 years ago, Dennis and I would like to exchange quotes from Joseph. And so, for example, one of my favorite ones, those just very short phrases. And so one of my favorite ones, I remember that very often you would come to his office and then try to tell him something, and he would look at you that, I mean, it was clear that he would think you saying complete rubbish. And then when we would ask him why, he would say, "You see, I have experience."
Sasha, it was only once. No. It was.
With you, it was once.
It happened only. It was a particular one time.
I know I know the event you're talking about, but to me it happened more than once. Probably I was saying rubbish more often than you. And another very common quote that I think we're still using all the time is that I mean, unfortunately I don't remember the name of the person, so Joseph would like to tell the story about when he was still in Moscow in the 70s. He was trying to do some calculation to some I mean, you definitely will tell me now who that person is. To some person who was an astronomer, and then Joseph said that somehow this work with this person would usually be done in the following would follow the following scenario: that Joseph would compute something, he would come to this guy, and the guy would say that somehow this calculations are all wrong, and Joseph would say that somehow they're not wrong, they're correct, and then this guy would think and said, now remember, I also have dust there. So the thing about dust is that I think Dennis and I were just using this quote all the time. So I think there were more, but I don't remember right now. So somehow I didn't prepare this in advance. But maybe Dennis will somehow pick this up. Okay, and in any case, thank you very much and happy birthday.
So actually, I wanted to say something in a different vein. I'll pick an example. So I was really impressed by Sasha Yomdin's talk. It's really, it was such a flashback to the course that Joseph told us about p-adic groups. It was amazing to see how I'm pretty certain that he taught something similar to Sasha Yomdin after. It was very clear how the seeds that Joseph planted in us bore fruit in Sasha's work. To me, it was such a clear kind of development and growth precisely in Joseph's spirit. How he broke the Peller-Wiener theorem in these two steps. First, the algebraic part, so abstract characterization of the algebraic part, and then manipulation will already something admissible. It really struck me as this kind of flashback to 25 years ago. It's just an example how Joseph's thinking propagates across mathematical generations. So I'll pass on to someone else.
Yeah, may I also say a couple of words?
Absolutely.
Yeah, so I want to tell a story. Actually, Joseph, even though I wasn't his student, he played a very important role in my life because he explained to me how to apply to graduate school in the United States. So the story was the following. So David Kashdan visited Moscow in 1988, and I met with him. So he gave me a short exam. I was 19 years old. And then he said that I should apply to Harvard to graduate school. But I didn't know how to do this. And so I applied only to one school, to Harvard. And also my recommendation letters, people who wrote them also didn't know how to write these letters. So the letter looked like this. Pavel studied analysis, algebra, geometry, and topology. I recommend him for graduate school at Harvard. And so, of course, I was not accepted, but Joseph was in the committee. And I think that David was in Israel for sabbatical that year. And so Joseph was on the committee. And so instead of just sending me a formal letter that I wasn't accepted, he actually called me and said, "You were not accepted. I will write you a letter and explain why and what you should do to be accepted next time." And then he wrote me a long letter, like 6 pages. Unfortunately, it has been lost in moving to US, where he explained to me that I should apply to many schools and that what recommendation letters should look like and how to choose places to apply and so on, many useful things. And I followed his advice, and next time I was accepted. I applied to 9 schools and I was accepted to 6. So then I came to Yale, and this was the start of my mathematical life in the US. So he was very generous this way. It was, of course, a lot of work to write this letter. And so I'm very grateful for that. Of course, regarding quotations from Joseph, of course, as a real rabbi, the quotations not only can be retold by his students, but also other people. So I hear from his students, I heard some of them as well. For example, one of them is that you should never do a calculation if you don't know what you want to obtain. I'm not sure that I always agree with it, but I always keep it in the back of my mind when I decide whether to do a calculation or not. So happy birthday, Joseph.
I doesn't agree with this either, but he definitely told us this many times. But 20 or 25 years later, I have a suspicion that he actually doesn't agree with this himself. I don't know.
Thank you.
I can tell you how this procedure was seen from this side. In this time that you learned, Joseph taught you, there was a time of a roman between Dennis and Natasha. And Natasha's mother is my friend. Actually, now it's Dennis' mother-in-law. And she told me, you know, it's so strange. Their professor, you and Dennis, only came from some trip. He only came to Israel, and boys, you and Dennis, already came to him to home. He only came and they already started to work. And I have to say that it's like this all the time, all his life. He only came anytime, any place, immediately children are coming and starting to learn, to work, to you know. It was strange for us because in our young years, it was not so acceptable that students come to a professor's house to study at home. It was only in university, in auditoriums and so on. But here, everything is much more simple and it's good.
I actually remember twice Joseph told me that I'm not good enough to be in graduate school. And so the first time it was actually in France, and we were in a supermarket, and I told him I didn't know what Earl Grey tea was. So, and the second time was I think this was actually in the quote, and we came. I was driving the car. No, maybe Dennis was driving the car.
I was driving. No. So you're distorting.
We came to the Weizmann Institute, and Dennis was trying to do parallel parking, and he couldn't. I think he couldn't. And then I said that I don't understand why somehow when you do parallel parking, why do you have to do it backwards? I mean, what's the difference between sort of going forward and Joseph says that somehow someone who has so little geometric intuition should not be in graduate school.
No. He said that I'm going to kick you out.
Well, okay, that's this. Oh, right.
Yeah. It was. I remember the phrase. Yes, and it was raining.
This I don't remember.
Yeah.
So I have two stories to tell. One is I've never told that story. When I started my postdoc with Joseph in Israel, I didn't know him well enough. I had not studied with him. So we started this seminar at Weizmann, and I had to give talks on my thesis. And he wouldn't let me finish a talk. He wouldn't even let me go halfway because I was not presenting things the right way. So I was writing down formulas and I was not saying what the formula meant. Of course, it was an easy formula, and if you sat down, you would understand what it meant, but he was refusing to do that. He forced me to, everybody knows this technique of Joseph's, that he forces you to think about things correctly, and then that changes the way that you're thinking. But in the beginning, I found it very, very frustrating. Joseph, I was thinking that maybe I came to the wrong place. Why? Maybe I cannot communicate with this person. Of course, you being Joseph Bernstein, I obviously obliged, and I sat down and thought about these things again. And of course, they started making much more sense. Since then, I have tried to do that with my students or other students and people around me. Just try to ask them elementary questions so that they can phrase things correctly, but me not being Joseph Bernstein, I really don't know how it looks to them and what impression I am giving by asking such questions. The second story is, I think, from the summer of 2006 or maybe 2007 in Germany. Joseph used to go to the Max Planck Institute almost every summer. Back then, he was invited by Bernhard Kreutz. They were working together. And it was about the time that Shamgar Gurevich and Roni Hadani had just finished their PhD, but they also visited there to talk to Joseph, and Rami and Dima were his students, so they were also there. And now I don't know what part of the story is true and what part is inflated a little bit, because, you know, Ronnie also likes to put some spice in the stories, but a story was told to me with Byzantine manipulations about trying to get access to Joseph. So the story that was told to me was that Bernhard was trying to disinvite as many of Joseph's students and postdocs as possible so that he could have Joseph for himself. And then Ronnie and Shamgar told me the tricks they made in order to be invited. But then somehow, even being invited there, they couldn't get to talk to Joseph very easily, because these young students, Dima and Rami, had perfected the technique of getting access to him. So, you know, for example, how Rami likes to walk around and talk and wave his hands. So he was doing this, but he was doing this in the corridors in a very strategic way, so that he would always have visual access to Joseph's door. So whenever his visitor stepped out, he would. So I was very happy, Dima, to hear that although you have an office next to Joseph, you have to wait the entire day to talk to him. It gave me some schadenfreude, and I was happy to hear that.
So indeed, I remember that summer very well. It was summer of 2007, and that summer made my career. And I would like to thank several people here, not only Joseph this time, also Bernard for organizing this, and Eitan Sayag for basically coaching us, because we came maybe 3 weeks before Joseph, and in those 3 weeks, Eitan almost replaced him to the extent that anyone can replace him. And Erez Lapid, who also helped us a bit that summer. And I want to tell one story. Okay, maybe we perfected this, but we still were not getting enough of him. And one day we came before him, and we knew when he came into the office, but first there were Ronnie and Shamgar, and then there were Yanis and Akshay inside. Okay, and then Sasha Goncharov came. And back then we didn't yet know that he's part of the family. So the first two couples, we were fine with them coming before us. They were older, but this guy, he didn't know what he was doing there. And it took an hour. So we knocked on the door, and Joseph said, "Come back in half an hour." Okay, we waited 45 minutes, and we knocked at the door. And Joseph said, "Come back in 20 minutes. So we waited 30 minutes, and we knocked at the door. And Sasha Goncharov opened and said, "Guys, I'm leaving in a week. Wait a bit." So I wanted to tell another story of my wife, who she was not a Joseph student, but she learned a course on algebraic geometry from him. And she told me that she didn't understand much, but she managed to write the home exam except one problem. And Joseph asked, "Oh, you did a very good exam, but why didn't you solve this problem?" She said, "Oh, I didn't understand this topic." "Very good, come to my office, I will explain to you." Then she didn't come, and he asked, "Why are you not coming?" I have to prepare to talk to you. I'm not ready yet. Joseph said, you will never be ready. Come tomorrow. And indeed, she came and she said that those 3 hours in your office were much more useful than the whole course, and really helped her to get back on track and do a thesis in algebraic geometry eventually. So I would like to thank you also on behalf of the students who just took your courses, not necessarily were students. And also on the same point, I would like to thank my wife for allowing me to sit here near the computer. And all this time she is with our kids, definitely. And all of our wives and families who allow this several hundreds of participants to be here. So I'd like to raise another glass, or twice the same glass, actually. L'chaim. So I said wives and families. Sasha Yomzin writes and husbands, so husbands included in families, but wives, husbands, and others.
Okay, I want to complement the story of
kids.
Dima and younger kids. So I'm not a student of Joseph, but I, for a long time, cooperated thanks to Peter, who really introduced me, although I even once saw Joseph in Moscow many years ago. So I would like to add one more quotation, which Joseph likes to use, is it's very difficult to prove a wrong theorem. It's possible, but it's very difficult. So this is and another one, the story.
Maybe I will tell more precisely that I think that's a very important thing, that before if I have some conjecture and so on, I'm trying to prove it, first I'm trying to disprove it. Because I know that if I want to prove a result which is wrong, it will take me so much time and so much effort that I will, it's just very difficult. So I have to be sure that it is correct by trying to disprove it. So I spent a lot of time trying to disprove things.
Okay, and another one is to complement this story about students trying to get into the office. At a certain point when Sasha and Dennis, and I forgot, there were many students. And again, I wasn't a student, but I was coming regularly to Tel Aviv to talk to Joseph and Eitan and so on. So I decided to make a joke. I brought this paper strip of numbers, glue it to Joseph's door and wrote, "Take a number." At that time, the line to the Joseph office was longer than now in the supermarket with a distance of 2 meters.
I remember this line, yeah.
Yeah, it was it's very important to take a number.
So I indeed spent several years in these lines. And they reminded me of something. So one of the favorite books of my childhood was The Three Musketeers by Dumas. And there they also described a line. It was the line to de Treville, the head of the king's musketeers. And the line was like this. It was on the stairs. And one musketeer was standing on top of the stairs with his bare sword. And he was defending from three musketeers staying downstairs. So he was staying higher, but there were three of them. And if anyone got even a slight wound, he would go to the end of the line. And if this would be the guy on the top, then the guy who wounded him would take his place. And if the door opens why it happens, then the one on top enters.
Dima, I
So
think
that was
is very correctly describes the situation with Joseph, but actually I just read The Three Musketeers with my daughter, and there's no such thing there.
Really?
No.
Okay, I read it. It was not an. I didn't.
In what language did you read it?
So,
in what language, Sasha? In what language did you read?
Both Russian and French simultaneously.
Oh,
wow. So, okay, I remember this from somewhere, and at least in this case, it was similar because we would definitely exchange mathematical questions. And several times it happened that my question was answered. And once it happened that it was not answered, but I got the person interested, so he would ask it along with his own question when he was inside, and then came out with an answer.
How often did you get wounded?
I still haven't recovered.
May I say something? Joseph was is regularly visiting the Max Planck, and typically he came for 2 months. And so you always talk about this 1 month when you all were there. And I also know the other month where the students were not there. So, and Ares said he's like a Zen master, and I would say he's like a monk. And so he walks around this Max Planck Institutes like in squares, like monks do. You ask him a question, and then he says, I have to think. And then he starts to walk. And so he goes upstairs and he comes down. And then after a while he walked, so he comes back with an answer. And once he was also in Hanover, and this is the university is in a big castle, and then Joseph was walking along these long alleys. Each time he had to think. So it was quite beautiful to watch him doing that. It was a little bit strange for the professors and my colleagues in Hanover, to see a person, walking around thinking, absent-minded in some way. So, and I had the great pleasure to work with Joseph 1 month. I think it was for me, a very beautiful time. Yeah, so he is in some sense a philosopher, I would say. So he always asks why. Why is it true? And this is, when I came to say something about myself to the Max Planck, they called me, okay, you are crazy, you always ask about why are things true? We don't do this nowadays. We just do mathematics. And internally, I always thought, okay, so they're all wrong. And so it was then very nice to see Joseph, that somebody, who always asks why. Why is it true? And I remember this. I showed him often things, and I said, hey, Joseph, here's something we might want to look at in the paper. And so then we looked at it together. One of his quotes is, I think it evaporates. Yeah, there's nothing in it. And so this is always this going to the very bottom of things, to the pure essence, which qualifies him, and which I think is so beautiful in talking to him in mathematics. So this determination, to go to the very bottom. And also, I would like to add one thing. Some sort of, it is, okay, we all know Harishchandra modules, and then everything has to be K. And so Joseph said, okay, you shouldn't think about K finite vectors. K finite vectors is not a good thing. And you should think about matrix coefficients of a reductive group differently. And so I think it's due to him, to use bump functions and Dirac approximations, which became an extremely powerful tool for analyzing, some sort of growth behavior. So it started with his work in Resnikov and so on. And I think it's also a very nice, very small and very elementary, but very important contribution. Okay, that's it. Thanks, Joseph. No, cheers.
Thank you. Thank you. And L'chaim.
So maybe I'm talking too much, but I'm slowly recalling all kind of memories. So one memory, I remember, I don't remember what it was about, but Joseph told us something, and I didn't understand why it is true. He said, oh, that's obvious. So I thought for an hour, I'm not getting this. Next time I asked why, I got a hint. Didn't help. Then next time I got a longer hint, and I thought all day, and I understood. And I came back, and I said, Joseph, I understand why this is true, but why is it obvious? And as for quotes, I remember one quote of Joseph, which is that all those difficulties with zeros and poles of n functions come from the fact that we are trying to trivialize a job which is not trivial. And that's why we get zeros and poles. I never understood what to do with this saying or how to materialize it or formalize it, but it keeps sitting in my mind as some goal, some high goal to once understand.
So waiting for a next hint.
Yeah, maybe I'll just say something brief. So, well, one thing, it will not be very original, but many people say this, but you know, both Joseph's influence on mathematics and this conference, I think, are really kind of in life often, you know, life is difficult and kind of confusing, but just a message that there is, you know, that it is possible to get to the bottom of things and then they eventually will be simple and beautiful. It's, you know, it's so good to be reminded of that from time to time. And in terms of story, I'll just repeat the story that I told on the previous birthday, but for me it's somehow so important that although it's a small episode. So there were these Friday seminars where, you know, where actually university was almost empty and there was no really problem of getting access to Joseph. So it was just basically us and him in the building. So this was perhaps the most productive time, like, and once I was fortunate to be on the bus with him, like when we were returning, I was going to Jerusalem where my mother lived at the time. So I was taking a bus from the campus to the train station where the bus was leaving from. And he started to explain me something about L functions, but, you know, unfortunately, so he was going somewhere further. And so my stop came and I was stupid enough to step from the bus on my stop before waiting for the explanation to finish. And so I asked him the following week what like to continue, but he already wasn't like, he lost the thread. And I mean, of course it was somewhere in his mind, but he wasn't sure what he was going to say. So I'm still hoping to continue this conversation someday and find out finally about the right way to think about L functions. Thank you.
Do you remember the number of the bus?
Yeah, it wasn't. It was. I remember it was a Dan bus, not Egged bus, but I don't remember.
Where to stay? At what stop to wait for the continuation?
I think Joseph once told me, I won't get his words quite right, but essentially that he didn't believe in L functions. And of course, I was very shocked at the time that he could prove so much about something without believing in it. But it was actually a very important comment in a way, that I could see that you could take some concept that was around for so long and I just took as fundamental and question it. And I found that very inspiring. And even now, the things I'm doing now, I'm trying to in a way, understand this question of Joseph, like, well, what, is the L function a fundamental object or not?
Let me explain. No, L function is absolutely fundamental object. That's just, it's interesting that my last year at Harvard, I taught number theory course. I decided to give proof of Dirichlet theorem, and somehow I realized that L functions are really fantastic central object. What I'm saying is that L functions not really function. It's section of some bundle probably. And L function means that we trivialize this function, trivialize this vector bundle. So this section, this vector bundle is very important, the section is very important. Its trivialization is not important. Okay, so that's what I meant. Not that L functions are not important. That L functions are absolutely central, I agree, but I think that the way they understood is not very correct.
If I can add sort of on that note, so it's maybe less deep, but I think something that determined a lot of my style of doing mathematics is when Joseph, said that he doesn't like spectral sequences. So I've never in my life used really spectral sequences explicitly, which, sometimes it could be kind of, many people do that and it helps them, but
maybe it's time to ask, Joseph, can you give us a hint? What is this with L functions? What is the torsor? Because I think many people raised this question already. So can you say something? What's the nature of?
I have a student who has written thesis about this right now. And yes, and I think that this is...
Wait, who?
Galdo.
Yeah.
You know him.
Okay. I know him, and he's here.
I think that he has some answer to this question. I cannot repeat it. It's for me too sophisticated.
I see. Okay. But because I'm really curious.
Yeah, okay. This is a feeling. I have just a feeling that this standard normalization of L function is not. It's just some normalization, some way to write. You're trying to write down some very important objects. You want to write down some explicit form. For this, you make some choices, and of course, these choices somehow they cloud the picture.
So what it's definitely true for partition functions on field theories. There, it's really have some kind of. You really have a determinant bundle, and your partition function is a section of that.
Yes.
That's clear. But for me, it's much less clear with L functions.
Yes. No, I don't know. It's just my feeling.
Dennis, there is, if you look at in the Bloch-Kato conjecture, it gives you a way to see that the L function gives you a section of the determinant of Galois cohomology. It fits exactly with that. Determinant of compactly supported Galois cohomology. The formal structure of the Bloch-Kato shows that, I mean, we don't have any other way to construct that section, but presumably that determinant is trivial and the L function is the generator.
I see.
So,
wow.
So this is implicit in Kato's papers, but it's not very prominent.
I wish we could continue because I'm really curious.
So since we switched to L functions as a way to celebrate Joseph, I have a question to Akshay about Akshay's lecture. Is it okay, guys?
A second, because I wanted to conclude the non-mathematical part with one remark. So, and then we'll switch to L functions completely. But I want to say that in the end of Peter's talk, I said that somehow I would like to continue this conference forever. And that was sort of, that was a pretty impulsive phrase, but I think that now I understand why I said what I actually meant. But I meant that I think that when I'm now thinking about sort of how graduate years, I think Dennis will agree that was a huge amount of romanticism about mathematics when we're sort of when we're graduate students of Joseph, and I think that I am definitely missing that romanticism, and I think that I have a suspicion that many people here are. I think that this conference was so successful because it brought back some of that romanticism in some way.
I totally, Sasha, exactly right. Expressed it exactly correctly. I mean, not expressed, it's just exactly the right sentiment. I think it's exactly that. So I also felt so inspired. It's just exactly like 25 years ago, whatever, 30.
Maybe this is this is a good result of this coronavirus, that now these conferences in Zoom will be popular, and you can do it every day, you know.
Maybe every week, not
maybe
every day.
now Joseph is taking part in seminar here in Jerusalem, also the seminar in Princeton, including Canada participants, and so on. And you don't know, you don't have to trip to go to airport to get the flight and so on and so on. Everything in here in home, and you can continue in your life and enjoy the real qualified meetings. And maybe it was to think to really to do it, because it came clear that you don't have to be physically together in some place. You can do your beloved mathematics sitting only in Zoom. And I know that you cannot live without your mathematics.
So I have to say goodbye because I have a meeting starting right now. So Joseph, thank you so much.
Thank you, Dennis.
And speaking of seminars, I wanted to say that we are going to revive our seminar at Weizmann starting next week, and Raphael will be our first speaker next Wednesday.
Okay.
Okay. About seminars. Excuse me, I want to take the right of speak now before you go to mathematics. Can you hear me?
Yeah, somebody.
I need to go soon because of family. Ivan, I think you called some echo.
You have an echo.
Yeah. Okay. So I want to say two things. One is about this conference, and another thing is a personal thing to Joseph. So let me start with the first one. So it was a wonderful conference, and I want to.
I think Ivan Cherednik needs to mute his microphone because there is a return.
Thank you. Oh, okay, much better now. Thank you. First about the conference, that was a wonderful conference, and I want to suggest, I don't know, maybe it's too much, but if this would extend as a weekly seminar, that would be just fantastic. So this is to the organizers to think about if you want to take this burden on yourself. But I think many people will appreciate it. And another thing, so again, sorry for bumping into this family celebration. I always feel a bit like an outsider, and for many years, but since early 2000s, I was a grad student, and I was traveling from Haifa to Tel Aviv once a week to, it was like pilgrim to sit in Bernstein seminars and to get some of the feelings and the mathematics that was, and to be a part of this wonderful, wonderful group. This was a very wonderful experience for me. And I think I didn't grow up in this community of this typical kind of mathematics, but Joseph, your mathematics and your style of mathematics influenced me very, very deeply. And I really, really want to thank you for this. And Mazal Tov for your birthday. And thank you for all of this. I have to leave now, so goodbye, guys. Cheers.
Can I say one thing quick?
Oh, very quick. Super conference. Thank you so much, guys. I really enjoyed it, and I enjoyed the end. So happy birthday! It was in April, but still, happy birthday, Joseph. I'm done. You can unmute me. You can mute me.
Thank you.
Ося, если ты нас слышишь, мы не очень понимаем. Днем рождения.
Привет.
Привет.
С днем рождения.
Привет.
Yes.
Hi. Hi, Patrick.
Yes. Something from Gelfand when I was young, that I was a very bad mathematician. And I learned the same thing from Joseph, but it was differently said. This is what more understandable when Joseph told me this. It was implicit in Joseph and it was explicit with Gelfand. So it was very explicit with Gelfand. So I had a very nice experience with Joseph also, and I'm happy to have attended this lecture. Thank you. Happy birthday.
Thank you.
Can I say something?
Absolutely.
So I wasn't a student of Bernstein. I'm not qualified, but I was hanging around with his students, with many of his students at that time, including the trio, Sasha Braverman and Roma and Denise. We had good time. We drank, or more precisely, I was watching them drinking, and it was kind of an anthropological experience, I should say, and. I don't remember all the anecdotes and they are not very important, but there was one thing which somehow is vaguely in my memory, and that has to do with Bernstein and music. And there was something, now I don't remember if I heard it from Bernstein himself or from one of his students, that Bernstein doesn't believe in score, in music scores, because he saw some score of something and it was in some how do you call it? I forgot how you call it in English. That you have the flat and the sharp signs, but it never get to the there was no B sharp in the score, and he just couldn't understand this. And I was surprised because he certainly should have thought about the principle of analytic continuation, but I'm still puzzled by it.
L'chaim.
Okay, so should we go back to conscious now? Or?
Я могу что-то сказать?
Bye-bye.
Sure. Vadik, you can say. Sure.
Я могу сказать.
Just show your face. Just show your face complete, so people will recognize you.
I normally it should be seen.
No, it's only half face.
I don't see myself. It's okay.
Yeah.
Yes.
Okay, I just, Osia, Iosif, Tamara, Osia, I just want to say happy birthday. It is very nice to meet you. And it was a wonderful conference. And I'm glad to see you and Tamara, you all as well. And Katya, Katya, пойди на секундочку. Скажи ему. My wife, Katya, wants also to say hello to you.
Привет,
И с
привет.
днем рождения.
С днем рождения.
Thank you very
Nice to
much.
see you.
It's really nice.
Okay, and it was very nice, and hope to see you many times again.
In person.
Sometime probably.
Sometime.
Probably. Yeah.
Okay, thank you. Спасибо.
Thanks.
Скажи спасибо всем, наверное.
So thanks to everybody. Okay, so.
Okay, let's talk about L functions. I have a question to Akshay. So you mentioned somebody is having the mic open. Okay. So you quoted our work with Joseph, and as you know, one of the strange things is that naturally there appears these periods which are not L function. When you square them or raise to higher powers, you get really long length L functions. But sometimes they are, sometimes they're not. How it corresponds to your picture that you propose to?
So you're talking about the phenomenon that the periods which give square roots of L functions, and and this is something that so it corresponds to the short answer is we don't have a very good understanding of it. I'm not sure I can actually say something that you don't know about it, except that perhaps that there is a dual phenomenon. This is that being the spectral side, that we can see under this duality that there's a dual phenomenon also on the automorphic side, which is related to metaplectic covers. So to phrase it very informally, you can ask which L functions admit a square root, so to speak. And certainly by the experiences that the only L functions that have a square root are ones with symplectic parameters. Okay, but that's certainly not sufficient. That is, the L function of a PGL2, a form on PGL2, which has a symplectic parameter, doesn't have a preferred square root to our understanding. And to phrase it very informally, it appears that I'm just saying this at a slightly heuristic level, but the property of having a square root is like giving a metaplectic lift of that symplectic parameter.
Metaplectic what?
It's of the same nature as that symplectic parameter lifting to the metaplectic group. Now it doesn't really make sense. The metaplectic group splits over the complex numbers, but that I think that somehow is the spirit of the thing that's going on. But I don't understand at a more detailed level.
Okay, and another question.
Precise. So suppose that you have a situation when you have a period and which is not an L function, but say its square is an L function. But if you look at the period itself, do you expect it to have similar analytic properties to the L function, like analytic continuation, things like this? Or
well, in those instances, it tends to be rigid, like it's the square root of an L function at a specific value.
At 1/2.
So yeah, so I don't know of examples where you can.
Can I make a comment? So,
sure.
I'm not a specialist, but so I heard something from Joseph Ayub about this question. So I was given a talk at his university about this Walpurgis periods, and there is a kind of conjecture about motifs which says that some motivic Galois group should be simply connected or something like this. And well, roughly it's about the fact that your H1 is, well, it should be kind of a motif, and there should be some motivic Galois group around which should be simply connected. And your orthogonal group is not. And this is why it appears. So there is a conjecture in the theory of motifs which says that something is simply connected. And maybe this is a point of view. But I don't know a precise formulation. Maybe somebody can clarify this.
Okay, I have one more very quick question. So in this triple product case, you have not one identity, but somehow two identities different, because you can embed, there are different chains, more than the two chains. What it corresponds to in your picture?
So that's, again, I don't understand, but there's something I can say. You can make kind of, based on these two chains, you can write down two different stacks that are kind of dual to that period, one for each chain, by sort of formally looking at them. And the surprising thing you find is that the stacks are not unrelated. They have the same core space. So I think, so you can definitely see some relationship on the spectral side a priori without knowing about this Gelfand thing, but they're not the same. And that's somehow, I think, a fundamental, have to figure out what is going on there.
Okay. And you expect your picture, of course, to include the Galois group, not only the dual group of what you're saying, right? Because these are examples with arithmetic looks completely bizarre.
Oh, sorry. If you're asking, do we understand issues about non-split things? We do not. We haven't reached that level. We think about everything split. I think Yanis has analyzed a little bit some examples, but we just haven't reached that point.
Okay, but is there a text of what all you're talking? Because I haven't seen, or it's still in the process.
We're working hard.
Okay.
But I'm taking I take inspiration from Joseph in this also.
You know, guys, I have a hard feeling that only real thing is in this world is mass. Really, I always had this fear, and now I'm sure. And it's good.
Actually, can I ask you another question about your talk? There's something in your talk. Yeah, I even asked you during the talk, and you answered me, but I still wasn't able to sort of repeat it. So this was, I mean, okay, in principle, all this is about some kind of particular examples of this symplectic duality, but something which before was sort of not really done in symplectic duality, in the sense that somehow your both sides are not conical, which is somehow in like traditional symplectic duality, this is people rarely consider this. But my precise question is the following. So you had this formula when I said that in general case, the period, or maybe square of the period, was equal to some summation over the fixed points. Now, I was not able to make that precise. I mean, what exactly is the right-hand side? So you said that somehow it's the fixed points respect. So you're computing period of some particular automorphic form. And first of all, this formula, is it local or global?
That formula is global. And I also, David Ben's V is here, so you might defer to him on any questions related to symplectic duality. He would have a better answer.
Let's just look at this formula. So somehow you want to say, so this is a global thing. So we have a global, have an automorphic form. To that you associate some global length parameter. And now you have this dual variety X check, and you want to sort of express the period of your form in terms of some summation of over some fixed points on that dual variety, right? And so in terms of some L functions associated, and I mean, there will be some sum of L functions, and that sum of L functions, the set which indexes the summation is the set of some fixed points. Now, first of all, can you say more precisely, it's the fixed points of what?
It's the, so in most classical cases, there's just one fixed point, because, at least for generic parameters. Yeah, sorry. So the fixed point is there's this Langland's the automorphic form is parameterized by a map from some Galois group into the dual group, and therefore that Galois group is acting on through that on the dual space.
Sorry, I didn't. So this how does the Galois group act on the dual space?
The dual space carries an action in the dual group, but now when we compute the period for a specific automorphic form, we have a parameter from that Galois group into that dual group. So it's acting through that. Now, a typical situation is this dual space. It maybe looks something like it's induced from vector space. So, or in simplest cases, it is just a vector space. Then for a generic parameter typically fixes only the origin, and you get the L function of that vector space. If it's induced from a vector space, the structure of induction forces the parameter to land in some smaller group, and then you get an L function for the smaller group. So that's the typical picture. There are a small number of cases where you have finite numbers of fixed points, but in most cases, the generic situation is just one fixed point.
Does it make sense when you have infinitely many fixed points?
The only examples that we have are these stacky examples. So there at the kind of the sort of rough level of analysis that I was talking about in the slide, that they look like they approximately work, but I don't have a huge supply of examples that we've thought about.
Okay, thank you. And another question is the following. So you have this,
that would be good. Yeah.
This quality is somehow, it's not really fun to write, in the sense that, so for example, depending on the situation, you get sort of different answers. So for example, the easiest case is this kind of case when you have a group, and you have, I mean, when your group is G times G, which acts on G by left and right multiplication, and then your Hamiltonian space is the cotangent bundle to the group, and your dual space is the cotangent bundle to the dual group as well. Sorry, you're muted.
Sorry, there's a mild twist on one side involving the Chevalier involution, but essentially, yes.
Okay. But then there's another example when the group is, say, JLN times JLN minus 1, and the subgroup is JLN minus 1 sitting diagonally. And then the quotient is again, I mean, then you're supposed to take cotangent bundle to the quotient, and which is again cotangent bundle to JLN. But in this case, the dual is something else.
Right, it's a.
So to what structure,
in that case, yeah.
What structure you actually associate this dual? I mean, it's not really associated to variety, it's associated to some other structure, which.
Well, the setup we have, the spherical, so those are different spherical varieties that you described. So the input in our thing is a spherical variety with some extra technical conditions that ensure, that morally speaking, ensure multiplicity 1.
Well, I mean, the variety is the same as the group, which is the group, which is
no, that's right. It's a pair, reductive group spherical variety.
But Sasha, this is the construction is a variant of something that you do, right? With these ring objects in the Satake category, right? I mean, if you have a spherical variety and you look at category of spherical sheaves on it, then out of this, you can construct a ring object in the Satake category, which is actually an associative factorization algebra in the Satake category. And take spec of that, that gives you an affine Hamiltonian G-dual space. So that's the affinization of the true answer. The true answer, there's no reason to expect it to be affine, but you can construct, so that's literally a functor. You can take a spherical variety and you can build out of it an affine Hamiltonian G-dual space. Now, you can try to do something Tanakian, something more clever to get not the affinization, but the actual dual, if you expect, but often the duals we expect are affine. So that's, you're happy there. But this is a functor. And again, it's kind of a variant of what you do with Finkelberg-Nakajima.
So I really think that if you start with this just variety and the group which is acting it, then the dual side is canonical, essentially.
It is a function, right? I mean, its duality is it's not about a spherical variety, right? This is not symplectic duality, right? It's S duality in 4 dimensions. So it's not a statement about Hamiltonian. It's not a statement about symplectic varieties. It's a statement about Hamiltonian group actions. And the S duality tells you expect roughly Hamiltonian G spaces and Hamiltonian G dual spaces to correspond. The symplectic duality, as you know, you get from that by kind of pairing with Whittaker on one side or kind of Neumann on the other. But the statement here is about Hamiltonian G spaces and Hamiltonian G dual spaces.
Okay, so basically at the first approximation, you're saying Hamiltonian G space, Hamiltonian G dual spaces should be the same. Okay.
That's right. That's what Guyot-Witten basically suggests to us. Right?
Okay.
But I think at least from number theory intuition, we have no picture of this beyond something very close to multiplicity 1.
But do you have in number theory, what kind of examples do you know when you really get the sum of L functions and not one L function?
Besides these weird stacky ones, there's a fairly small number. I think it's only one. I don't think any examples have really been studied classically. But maybe there's one example involving the symplectic group. Yanis, do you remember what it is?
Well, there is a conjectural case, the quotient of SO2n plus 1 by GLN, the Levy GLN, where you would expect a sum of 2 L functions associated to smaller symplectic groups. But already the Itino Ikeda formula, there are these small rational factors in front of the Euler product that can be interpreted. Maybe it's a little bit hard to explain now, but already in the group case, let's say that we have a group whose dual group is, so a semi-simple group whose dual group is not, so a semi-simple but not simply connected group, so its dual group is not adjoint. Take a discrete Langlands parameter, then its centralizer is finite. So you're gonna see a finite number of fixed points on the dual Hamiltonian space. Of course, all of them will contribute the same L function, but you're going to see this small number in front of the L function. This, if you normalize things correctly, you're going to see this small number, which is the number of the centralizer, the order of the centralizer of the Langlands parameter.
Okay, yeah, I see. That's a good example, actually. Thank you.
Can I change the subject?
Of course.
Yes.
Yeah. I was trying to say something earlier, but the thing I was doing from my laptop didn't work. Now I'm using my iPhone, and it seems that I'm able to talk. I wanted to say something about Joseph's and his stuff on Eisenstein series. This was 2002. Peter and I had a conference on the L functions, and one of the central speakers there was Joseph. And he came, he gave 5 lectures, and of course, the agenda behind it was that we wanted him to write his proof. And of course, didn't happen. We kept writing to him and he didn't do it. Eventually, we had to go ahead with the book, and the book was published. But now I'm so delighted that it is out with errors on it. So I really like to drink to him for the wonderful work he has done for mathematics over all these so many years, and also to the fact that this proof is finally out. Happy birthday, Joseph. I had a glass of wine. I was trying to drink it earlier, but I couldn't connect. Happy birthday, and thank you to the organizers for doing such a wonderful job. Thank you.
Thank you, Ferdinand.
Thank you.
So I'm gonna have to run soon.
Really run? You are running?
Not run, I mean, go have another meeting. Thanks for organizing this.
Thank you for coming.
To another.
Yeah. Thank you so much. That's a wonderful conference.
Thank you.
Thanks,
organizers.
I have a technical question to the organizers. What happens to the recordings of the talks?
What?
What happens to the recordings of the talks?
So they should be on the
on the YouTube channel. There is a link from the conference website to a YouTube channel. You should be able to find them. It's one recording for a day with all the 4 hours, but of course you can use the timeline to choose the correct talk.
You mean that if you go to the conference website and click on YouTube channel, that you will see the recordings every day?
Yes.
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 So actually this channel includes recordings of this conference and recordings of the conference 3 years ago, but you will be able to distinguish.
Is this chat also going on the YouTube stream?
So, the chat not, but we are publishing the chat. So after each talk, we put slides, notes, and the chat. So we already put this for the three previous days, and probably tomorrow we will try to put it for today's talks. So in the chat, we only put the public messages and not the private ones, unless we make a mistake. I edit this by hands.
So people in CNRS are forbidden to use Zoom. That was the...
Right.
I don't think they're forbidden. My understanding was that they're forbidden to organize seminars in Zoom, but no, they're not. It's not that
we said that they cannot use it. I don't know what it means.
I recently gave a talk using Zoom, so that's.
Well, that's a difference.
Погоди, Андрей, в каком смысле я в СНРС? That's okay.
Now we caught you.
In some sense, but I'm not using you. You haven't seen me. I haven't seen.
We haven't seen you. Only half of you. Only half of you.
Because I'm half in CNRS.
So I want to say thank you to everybody and thanks to organizers of this wonderful conference. Very interesting. And I would like to to listen to lectures once more and to try to understand them, because I couldn't understand on the spot. It took too difficult.
But I mean, I think the idea of continuing this as a weekly seminar is really
tempting.
According as you've seen at dinner, it could be very useful. The first possibility to slide to your math themes, you used it and you go there and you more enjoyed it. So.
Okay.
Okay, thank you.
Okay, thank you. Now you can continue one-on-one.
For talking.
Happy birthday, Joseph.
Thank
Bye.
you, Akshay.
Happy
Bye,
birthday,
Sasha.
Joseph.
Thank you, everyone.
Thank
Thank you, Dorian, for coming.
Happy birthday. Thanks to organizing.
Bye.
You go also.
Thank you.
Bye-bye.
Bye.
Okay.
Dima.
Yes.
Yeah, I just had lunch. I'm back. I guess thanks again. I just thought I'd say goodbye.
Oh, it's our pleasure. Thank you for coming and for talking.
Yeah, it's a great thing you did there, and gives a lot of positivity to people who around the world. Anyway, well done.
Thank you.
Keep well.
Thanks for collaborating and for a wonderful talk.
Yeah, thank you. Well, I look forward to when I can get there physically. I was quite looking forward to actually traveling to Israel. Right now, Israel looks quite good, actually, right?
Yes, it does. Yes. Looks like we are getting out of it.
Yeah. All right. Anyway, well done and keep well.
Wishing you the same. Hope you can come soon.
Yeah. See you.
See you. So, Jozo, I hope Rami has the photo you're talking about. I couldn't find it right now. But it was very good to see you.
Yeah. I remember we have this photo taken in Jerusalem. But
Yeah, we did. Which reminds me that I'm not sure I emailed Toma. I emailed all kind of people, and I cannot remember. No, I don't see him here. It's my fault. Okay, thank you for coming. Bye.